Connect to the cloud. All right, and then I'm going to change my Zoom real quick. So my microphone is the hello, hello. Okay, good. All right. So hey, welcome to the workshop. I'm Scott Cunningham. I'm the host or the lecturer for the workshop. And want to tell you a little bit about the where you can find stuff before we get started. So I'm gonna go ahead and share my screen. Okay, I'm gonna share my screen and kind of give you some stuff. My computer's acting weird today for some reason, but hold on. Okay, so then let me show you what we need here. Oops, what am I doing here? Oh yeah, mixtape sessions. So all right, so I'm gonna put this in the chat because not everybody may be on the Discord, but I'll explain that in a second. So this is kind of the mixtape sessions large GitHub repositories. This is where all of them are. I do Causal Inference 1 and 2, and I have a Causal Inference 3 that is not up here. And then we have some like shorter tracks that I have guests come and do. This semester, we just have one scheduled. We've been having like 18, and it's like really intense. And so plus Kyle Butts, who does this with me, is on the job market. So we're sort of slimming it down because for this spring, and then we'll probably pick it back up in the fall. We just kind of want to get a sense of what demand is. So, but we're going to have a new one. So this is where this is sort of the thing, but we're going to be here. Okay. So I'm going to put this in chat. Okay. And then I'm also put it under under general in the Discord, which I'll explain in just a second. All right. So we're going to be in lab. No, sorry. We're going to be in slides here, and we're going to be doing foundations.pdf. All right. We're going to do foundations.pdf, and that should be something I just uploaded. Should be something I just pushed. So let's, it should say that. Let's see, does it say tons of stuff? Tons of updates. Okay. So I'm gonna go ahead and open mine so you can see it. I do not know why probably over the break, I'll have to reboot my computer or something. Something's going really slow. So we're gonna do foundations. All right. And we'll go ahead and open it up. And then before I open it up though, we are using Discord for our main way of communicating. There's 126 of us on the call. And I encourage you to do the Discord because the Discord creates a permanent record of everything. And so I'm going to give you the link here. It's a lot like Slack. It's free. And so you can get on it. But, you know, my preference is you get on it, but I can't make you do it. So, and then Jersica asked, do you know how to get all material in readings at once? The only way you can really, that I know of, Jersica, to get everything is to clone it, or you can download the zip right here. So if you want to download the zip, you can do that if you want to, and then it'll just kind of give you this massive download. But you can also go ahead and use this as an opportunity to do a little GitHub stuff, but you know, not everybody wants to do that. So you can do it that way. All right, so let me go ahead and open and get it started. Okay, so we got 5 things here that we're gonna do in this first deck of slides. We're gonna see how far we can get today. We'll definitely get through this deck, and then we're gonna get into this material I don't call it, it's called unconfoundedness. So we're going to do kind of two things today. The goal, two things today, kind of a brief discuss, or not a brief, but a discussion of the causal inference theoretical framework. And then we're going to look at covariates as a way of solving the problem of causal inference. There's going to be several ways that we solve the problem of causal inference, but today is going to be about covariates and randomized control trials. All right. So my name's Scott Cunningham. You can call me Scott. I'm a professor of economics at Baylor University, which is in kind of it's called Central Texas. For those that aren't in the United States, Texas is a big state that's we've kind of got 3 or 4 big states, and Texas is one of the big ones in terms of overall mass, geographic mass, and population. So I live in central parts of Texas, and author of a book called Causal Inference, the mixtape, and I organized this mixtape sessions platform with Kyle Butts, who's a University of Colorado Boulder doctoral student, and to basically kind of what I call solve a market problem where not everybody gets this training in their PhD programs, whether it's economics or not economics, or they don't get it in industry. There's lots of reasons for it. I'm going to kind of tell you, because causal inference that we're going to discuss is a particular influential branch of statistics and econometrics, and not every program historically teaches this material, even though this material is kind of widely known to be crucially important, not just scientifically, but even just kind of in your day job, whatever your day job is, if it's publishing or academic articles, doing government work, or something in industry. So it's really, really important area. And it's not always taught. And if it's not always taught and it's a really important area, then, you need to find ways to learn it. And the mixtape sessions platform is a way of trying to, try to do that. So I love economics. For those that are not in economics, everybody gets to love the stuff they love. And I love the field of economics. I love the field of econometrics. And I love causal inference. And so I run these workshops all over the world, both online or in person, and they're about kind of core ideas of causal inference. I try to get us up to a reasonable advanced level on these, but some of the more specific ones that are taught by people like Peter Hall or Ariel Pecos or any of these others, those are even more methodological frontiers. Okay. So the online workshops are really helpful. There's a lot of stuff you can do online that actually isn't as easy to do in classes, like coding together and things like that. Plus you get the recordings and you get all the slides, and you get the solution key, and you get all these readings. So mixtape sessions is really meant to be kind of as close to a public good as it can be. The only club good parts of it that club good, meaning the stuff that only you get, is the experience of the 4-day, the recordings, and the Discord channel. That's really the only things that the people that paid for this get. Everyone else on the whole planet gets the GitHub repository if they want to do it. And that's kind of the goal. The goal is to just try to, not have as many haves and have-nots on these things, but provide a bridge. So it's an old field. Causal inference is an old field, going back, depending on how you want to date it, going back to antiquity with Aristotle. But in terms of practical science, it's maybe 100 years old, less. Actually, no, it's the 100-year anniversary, right? 1924. I think that's right. Yeah, 1924. It's the first time I've thought of it. This is the 100-year anniversary of what you might consider to be the start of the design-based causal inference, right? So it's an old field, increasingly is drawing people into it, and it's won, recently just a bunch of big awards, including the Nobel Prize in 2021. You could say it's not the first time, though, something like causal inference is won, but there's kind of the stuff we're doing in this workshop won 2 years ago, and then there was in statistics, Jamie Robbins and others won the inaugural, I can never remember the name of it, the inaugural statistics Nobel Prize, and it was for causal inference. So it's a very influential, area. And, with those prizes, and even Uta Pearl's winning in 2014 of the Turing Award in computer science, it's just really gotten on the map, and it's not safe to avoid it. It's not safe to avoid it because it's becoming increasingly even something that's screened on in industry. Okay, so that's what we're hoping to do. So we're going to workshop together. Yeah, Nita says barely covered in grad school. Econometrics was one of my fields. I graduated in 07. Econometrics was my field, and I don't think I heard the word causality one time. So in econometrics traditionally and statistics traditionally, you did not talk about causality. Now that's not really true, but it was true for a long time. You would talk in a different way, but you wouldn't talk about causality except in the experiments. And for many of us, we might not have learned experiments. I never learned experiments. I don't even remember reading a paper on experiments. The last time before graduate school, well, the last time I'd even thought about an experiment was when I was a kid in the 5th grade, when I went to the state fair in Mississippi for an experiment I did. I mean, it just wasn't really a part of a lot of our training, which in some ways our training was more sophisticated and more difficult and more technical than the kind of stuff we're going to do now. And yet this stuff has become extremely influential. So we're going to workshop together for 4 days, 9 a.m. Central Standard Time. I know a lot of you many of you are in India and parts of Europe, and it starts to be late for you. So you get the recordings approximately 2 to 3 hours at the end of the day, which is 5 p.m. Central Standard Time. So it's 9 a.m. my time right now. And so at 5 p.m. we'll end. Zoom has to compile it. Takes me about 2 hours if it does it at the cloud, but I'm increasingly nervous about compiling on the local machines ever since I moved to this new house. And I'm not yet positive. I have the expensive internet, but I don't really know what'll happen. So I do it to the cloud now. And that takes longer. And then you have to upload it to Vimeo, which is the platform for storing the videos. And you get permanent access to the recordings. It's password protected, permanent access to the recordings. If ever I stop doing this stuff, I'll send out an email and you'll just be able to get the recordings yourself. You'll just get to download it. So we have every hour on the hour, 15-minute break, except for twice, leading into our 1 hour break at lunch. And then in the last hour of the day, we go a full hour. And so at lunchtime, which is in 3 hours, we'll have a 1 hour break, and then we'll come back, and then we will, at the end of the day, be done. So I teach in a very different way. So if you take these workshops with a true econometrician, and a true econometrician, in my opinion, or a statistician, or anything like that, they're not just doing applied papers. I write applied papers, and then I write materials that explains causal inference, but I'm not an econometrician. And to be an econometrician, you really have to have published in econometrics journals. I don't do that. And I don't consider myself an econometrician. I consider myself more of like an econometrics journalist, or like an econometrics, teacher. So that's different. So I tend to emphasize it. I tend to teach differently than those people. I emphasize a lot of intuition. I emphasize a lot of like the actual mechanics of the calculations, even using spreadsheets. I kind of am of the personal opinion that people like us that kind of work with computers and programs a lot, spreadsheets are actually, we all use them probably more than we use R or Stata or Python. And so I try to use them a much. My thought is, if I can understand something using a spreadsheet, I probably understand it pretty well. But I can do a lot of stuff in Stata and R and Python that, I might only have a very dim understanding of what's under the hood. So I try to do as many of those kind of raw calculations as I can. I teach a lot of things about the meaning of stuff. What exactly do these things we're doing mean in plain language? I try to imagine, not very successful doing this, but I try to imagine, well, what if I needed to explain this to my mom, an intelligent layperson? I'm always kind of striving to be like that, because my thought is, if you can do that, you have really good understanding. You can explain this to an intelligent layperson. So I try to do that. And I talk a lot in terms of the assumptions. I talk a lot in terms of the parameters, as I'll explain what that means. And then I talk a lot about code. I'm going to share a lot of code. We're going to go through code together. And I'm a big advocate for data visualization. All right. So I try to cover all the parts of causal inference that arguably really is a necessary input and a necessary output for creating a manuscript, whether that's in academia or whether that's not in academia. Whatever the equivalent of a manuscript would be, it might be a memo or a deck or something like that. In industry, I want you to come away with some, enough of the art and the science explained to you, so that if you don't get it on the 4-day, you can go back to the recordings. And if you don't get it through the recordings, you can get it through the Substacks, and you can get it on the podcast, and you can get it, in the book, and you can just get it a lot of different ways. That's the goal, though, is that, we're not going to actually learn the writing part of writing a manuscript. Although I have had people teach workshops that's focused on that. Dan Reese and Mark Anderson have one that's like that. But I want to leave you with that, at least as a ladder to go there. Okay. So I'm different. I'm a different kind of person in how I teach. There's a level of enthusiasm that tends to build throughout the day. I get a lot of personal satisfaction, joy, even from explaining this stuff and connecting with y'all. But I'm not an econometrician. And so I tend to take there's the long way. You can take the scenic route. If you want to drive back from, where you went to vacation, you can either get on the highway and get there fast, or you can take the scenic route. And the scenic route takes you longer, but you start to maybe appreciate some of the landscape a little bit more. So I tend to take the scenic route without trying to sacrifice any of the technical parts. So I rely a lot on even things like interviews with the authors of some of this work. I tend to do that even a lot. Okay. So my goals, you might say my pedagogical goals, are what I kind of call 3 C's, 3 words that start with the letter C: confidence, comprehension, and competency. Confidence is what I consider to be a feeling. It's like self-esteem. Okay. So it's like a feeling that you feel, where you feel like you belong. That's what I want you to feel. I want you to feel like you belong in the room, wherever you are. Okay. You might not know everything that a person is saying. I mean, obviously, if you are in the room and people are presenting new things, you're learning, right? But that's not the same thing. Being uninformed about, being uninformed about what people are teaching is different than not feeling confident and not feeling like you should be there. Okay. And so my goal is I want you to have at the end of it, that feeling. And the way that you get that feeling is you have enough base knowledge that it just kind of like it's demystified a little bit and it's not so intimidating because you feel like you understand a lot of the big picture and even a lot of details. When you have like that, you might not be the fastest runner in the race, but you're prepared for the race. You've trained and you feel ready. You feel ready to run a race, and you're not intimidated by any of the other runners. You're going to do your best. So that's one. Second is comprehension. Okay. I want you to learn ideas, learn concepts. That takes a little bit more effort. That you can't be as passive about. So you've got to put in the work to understand the concepts and the specifics. And some of that's done in the class, some of that's done when you ask questions on the Discord or in the chat, and I'll answer them. And some of it's in the homework, and some of it's in, just sitting down with a pen and paper and just kind of working through some stuff, or, so that's a big part of it. And then last is competency. Competency is, the skills that will let you to actually do this stuff. This is not philosophy. This isn't like an art history class. This is more like an art class. This is like a good, this isn't a theory of, jazz. This is like playing jazz. Okay. So our goal in this is not to create econometricians, although some of you may, or statisticians, although some of you may be on that route to do that. Our goal is to help you do empirical work practically. It's practical. It's a practical class. And to be a practical class, you have to have some programming syntax in Stata R and in Python. Okay. Because I want it to be that later you can apply this stuff in your own work and both make progress in the questions that you have and, practically also to, have more of the kind of career that you want to have, whatever that means. Okay. So we're going to communicate with each other regularly in the Discord channel. If you can get on there, that'd be great. I'm going to be monitoring it as much as I can. Oh, really? It said you can't do it? Huh. I don't know why. Check your email, Sydney, and see if something's different. It says it's letting me. I got about 75 people in there, but I don't understand why. If you can't get on, don't worry about it. But if you can, that'd be great. And you can get on, you can try to troubleshoot it later. Maybe ask ChatGPT or something. So we're going to communicate with each other. I'll try to double it up, but encourage you to talk to each other, encourage you to go into the networking and getting to know each other thing. So the networking and getting to know, what is that? Problem report for TV. All right, skip that. Here, people are kind of getting to know each other. I encourage you to get to know each other. Okay. And just network. I've not really had like, people becoming, I don't know, maybe people are becoming co-authors. I have no idea, but this is a time to meet each other, just make some acquaintances and ask people. And I encourage you in the Discord to ask questions. And if you think you know the answer, take a stab at an answer. And we all just kind of are going to be on the same page that, we're all trying to help each other. We're all trying to help each other. So, if you think you know the answer, but you're not really sure, just do it anyway. All right. Just kind of the goal, I think, is to create a conversation. So, all right, that's it. So here we go. Here's what we're doing. Oh, that's day 2. I'm doing graphs. All right. I was wondering, I was like, man, I didn't know I was going to cover all that. So today we're going to cover foundations and graphs. And then day 2, we're going to continue graphs and this material called unconfoundedness. Okay. And then number 3, day 3, next weekend, next Saturday, we're going to do instrumental variables. And then day 4, we're going to do regression discontinuity design. So it's 4 things that we're going to cover. We don't cover difference and differences. And the reason we don't cover difference and differences is that it has, probably some of you know, it has kind of ballooned over the last 5 years and just been overwhelming. Okay. And so we now have 4 days of lectures on it. And I also have, and I'll don't have it right now, but I also have Causal Inference 3, which I think is, I don't know what, here it is, Causal Inference 3. So we also have Causal Inference 3, and that's going to be on synthetic control. It's just kind of really sprawled the areas. Once diff and diff underwent its kind of like radical, like credibility revolution for itself. Once that happened, it just got to be impossible to cover it without just, not really being fair to the material. So I don't do it. I do it in Causal Inference 2, and it can be a little bit slower and deliberate. All right, let's get started. Anybody have any questions? Anybody have any questions before we get started? AI economist, you're saying something? Welcome, Thet. Welcome, Grain. Let's see. All right, I'm gonna go ahead and start. And AI economist, I see you typing, but I can answer in a minute. All right, let's look at these foundational ideas. All right. So there's a difference between causality in my mind. Okay. There's a difference between causality and causal inference. All right. And causality, so like in the field of philosophy, okay, in the field of philosophy, there's 3 what you would call branches. There's a branch called ethics. It's like, how should we live? Normative things like aesthetics and stuff like that. That's all judgments. Those are all, branches of ethics or just kind of normative concepts. And then there's something called metaphysics, or sometimes called ontology, which is has to do with, the nature of reality. Okay. And experience itself. And then the last is an area called epistemology. And epistemology is a theory of knowledge. All right. The source of knowledge and, what constitutes what you might call a reasonable belief or a true belief, kind of at a deep, deep level. Causality and causal inference are obviously very connected to each other. But one has to do with like the nature of reality. What does it mean for what is cause and effect? And then one has to do with what does it mean to have a belief about those cause and effect? What does it mean to have a belief about some cause and effect that's warranted? A warranted belief. All right. What is it that makes a belief that I have about cause and effect to be like a reliable, credible, trustworthy, reasonable kind of belief to hold? They're not exactly the same when you think about it. Causality doesn't seem like it like exists in the mind as much as it kind of exists in reality. But causal inference, has to do with like, should you believe something is causal? We are not a philosophy class workshop. We're this one. We're talking about the roles of data and models that allow us to draw inferences or, conclusions, rather, causal conclusions about, events that occur and then things that happened also. Okay. So they all have these common sources, though. They all have these common sources in philosophy. But in the 20th century, they kind of like moved into statistics and econometrics. And then we're going to focus mainly on a particular stream of thought in statistics called the experimental design tradition. Even though we're not going to do any lab experiments, a lot of what we cover is this experimental design tradition. And that sometimes having those phrases, in my experience, sometimes having those phrases to kind of put a box about something is really helpful, because then you're like, okay, well, whatever this other stuff I learned in graduate school is, or whatever this other stuff that I'm learning right now, I don't have to like worry about how this fits with that. I can just for now have like a box. I can think about entertainment um, as movies and television shows and novels and plays, or I can think about television shows as things like, comedies and serialized dramas. You can kind of like break them out, and you don't have to put things in competition with each other. You just sort of know, oh, okay, I'm just going to learn about the comedy and not really today learn about dramas, or I'm going to listen to rock and roll and not jazz. That's kind of the idea. All right. So the experimental design tradition is like rock and roll. It's like a particular genre or a particular kind of approach to causal inference that was developed 100 years ago. All right. And we're going to use the potential outcomes framework for doing causal inference. And the reason we use the potential outcomes framework isn't because it's better, isn't because it's true. Okay. It's because it is the what you would call lingua franca, the main statistical language used for causal inference in economics, statistics, and the entire social sciences. Pretty much. Pretty much. It has become, because it is so crystal clear, it is crystal clear exactly what a causal effect is, and it allows you to build up meaningful definitions of aggregate causal parameters. Makes it really intuitive. Whereas a lot of the time, those of us that didn't get this training in graduate school, we would pass our tests, we would do our homework assignments, we would do all that stuff, and actually defining what a causal effect would be, it would be kind of hard, because it would kind of always be embedded inside a regression model. And what we're going to do is we're going to free it from regression models. We're going to show how it maps onto a regression model, but it's not synonymous with a beta coefficient. Okay, it's not the same thing. All right, so just kind of briefly say, what I want to say here. Okay, hold on. All right, so I'm gonna kind of show you this. So this right here is probably like a typical class you would take in graduate school. It'd be like, usually it would probably be there's like the stats econometrics classes that you might take. And in the stats econometrics classes, you might get all three of these. Okay, you might get all three of these. You might get like OLS, Logit, Probit, like structural VAR or time series forecasting, ANOVA, like there's all this stuff. But then you might also get the stuff we're doing in this class. Diff and diff, instrumental variables, propensity score, RD, and you might also cover RCTs. Okay, basically you might cover randomized control trials, and that might be all. They might all be covered in the same class. Or those of you from industry, or those of you in a more advanced classes, you might learn. You might take a class, or just maybe it's not even take a class. You might just invest in a lot of training in machine learning. And machine learning might be things like boosting, penalized regressions, but then it also might be causal forests and multi-arm bandits and all this other stuff. All right, so you got like all these things which are almost kind of like classes or like methods, all right, or like they're classes, and they'll all be grouped together. That's what I'll say. Econometrics will group all this. Statistics will group all of it. But these classes may sort of be, they may not have any machine learning. Okay. All right. So within that too, you've got basically two two types of functions of these methods. There's two types of functions, purposes to the methods. One is you'll have methods that you're learning where the sole purpose of the method is to predict something. Okay. And that would be these. In the stats classes, that would be things like OLS, logits, logistic regressions, time series forecasting, ANOVA. And then over here in machine learning, that might be things like neural nets. That might be things like boosting, decision trees, random forests, all this kind of stuff. But they're not technically causal. And causal will be this stuff. Okay. It'll be this stuff right here. And what we're going to be doing is, and I'm sorry, this is getting kind of messy now. What we're going to be doing is really just this. All right. That's the only thing that we're going to be doing. We're just going to be doing, we're not going to be doing any prediction, and we're not really going to be doing any machine learning causal inference. I have people that have been teaching those things. Brigham Franzen has historically taught 2 machine learning causal inference workshops. And we're not, I may ask him to do one in the spring. Kyle's kind of got to clear the job market a little bit before I feel comfortable asking Kyle to set up a bunch, but I might reach out to him and do that. So we're just going to do this. We're just going to do this. The only things that we're going to do are, we're not going to do diff and diff. We're just going to do IV, propensity score matching, regression discontinuity, or we're going to do IV unconfoundedness, regression discontinuity design, randomized control trials. That's what we're going to do. Okay. And we won't go into, and it doesn't mean that these other things aren't important. It's just that, that's what this class is about. Okay. So what's the difference between traditional prediction and causal inference? They're actually both forms of prediction, but where they differ is what objects they are trying to predict. Okay. Prediction is trying to detect patterns in the data and then fit these functional relationships between the variables with a high degree of accuracy so that it can predict out of sample with a high degree of accuracy. There's lots of different things that you use and that take advantage of certain properties of the data set. And so sometimes one is particularly accurate over another, and then in another data set, it'll be the exact opposite, or it'll be some third approach. Okay. So there's, there's various tools that you're using with traditional prediction to kind of judge the quality of the prediction. And you're not doing any of that stuff in causal inference. Even old school statistics like the R squared, okay? That would be things that are really valuable in traditional prediction, and they are useless in causal inference because causal inference is not about predicting outcomes. Not exactly, okay? So here would be an example. A doctor looks at a patient's chart and they want to predict whether or not they have heart disease. They use a lot of data. They use a lot of measurements. And then they say, we think you have heart disease. We think you have cancer. We think you have a melanoma. Or you write a book and the publisher wants to kind of make a prediction, or not even that. Maybe the publisher speaks with you and wants to predict how many books you're going to sell. Okay. And he's got to make some prediction. So here's what makes it different. This person either has heart disease or doesn't. It either has it or doesn't. Okay. And it's not heart disease based on like eating a particular kind of diet your whole life. And it's not heart disease based on your age, or like it's not heart disease based on some action necessarily. It's just saying, given the world in which we're in, I can't tell that this person has heart disease, but maybe I can guess with some reasonable level of accuracy. Okay, so it's like a prediction of either something that is right now, but you have missing data on it, or something that's about to happen, like being a meteorologist trying to predict if it's going to rain today. Versus, so here's the thing. This is obviously very important. This is obviously very important. Traditional prediction is extremely important. It's just not the same thing as causal inference. Causal inference is a type of prediction, but it's a prediction of an object that doesn't exist. It's a prediction of something called a counterfactual. And that counterfactual is associated with choices that are done, policies, or certain kinds of actions that are taken. And in order to evaluate whether or not the action had some effect, you have to basically do a particular kind of prediction, which is you have to predict what would have happened had that choice not been made. And that's a fictional quantity. And so the things that make causal inference a reasonable, warranted belief are different than the things that make prediction a warranted belief. Okay. So causal inference takes that predicted or imputed, you'll hear me say that more probably, takes that imputed counterfactual and then constructs a causal effect that we hope will tell us about the future, but it's the future associated with an action, not the future associated with the world as it already is. Okay, so it's a little bit different. It's a little bit different. And we're going to unpack that. We're not going to really get into this, but we're only going to talk about this and hopefully unpack it. Okay. All right. Think about all that stuff. Let's take a short break and we'll be right back. I played music over the intermission. It makes me feel, gives me the energy. So if you don't like the music, just mute it. Come back in 15 minutes. Okay. All right. I'll be right back. Okay. I just noticed confirm your speaking language. Okay. That's what I'm doing. All right. So stop summary, AI companion. Oh, I never forgot to do the AI companion. Shoot. Okay. Well, now there's an AI companion. I haven't done it for 45 minutes. Well, haven't done it for 45 minutes, but now there's an AI companion and you should be able to look at it. I apologize. I think you can ask it questions. Actually have never done it, but I think you can, and then like converse. All right. And so let's look at sort of these questions real quick. Nita asked, just putting this here to discuss the support. If causal inference is used for counterfactuals, is it useful for examining the effective adoption of legal rules, their effects, comparing that to the path not taken? That is literally one of the main things it's used for. We just call that like a treatment or a policy, and that's that's kind of a general term, but that's one of the things we'll look at. Well, we won't look at that necessarily oftentimes that's more used in the diff and diff class and the synthetic control class, but nevertheless, yes. Miguel says, what if you predict the counterfactual using regression modeling and stop there? That is, you do not take in a second step, the predicted counterfactual to construct a causal effect. Miguel, that's a little bit more of a complicated answer that I could give. Regression models take on causal interpretations sometimes and sometimes not. And so it's not, when I say like you're estimating a predicted counterfactual. So when I said this right here, okay, when I said it's going to take that predicted or imputed counterfactual and construct it, I know it sounds as though it's doing it in 2 steps. Okay, it sounds like that's what I meant. But it's not exact. It doesn't require it happen in 2 steps. There are methods that use 2 steps, and then there are methods that just do it instantly. But what I'm trying to say is that even if it does it instantly in one fell swoop, like a regression model, which, like you said, does not go in multiple steps, it just minimizes a particular function, a particular objective function, some of the squared residuals, minimizes it, gets a line. Under what conditions can that line be interpreted as a causal effect? And under what conditions can that line simply be interpreted as a oh, it's in day one. Okay, thank you. And it just is a prediction. Everyone, let's see if we can get a little, let's get a little further and let's see if it helps, okay? Because it's a slow unpacking, okay? Prediction is more of an understanding what happened earlier. Ravi, let's hold off, because I actually typically think of them in the opposite. Like a meteorologist is predicting the future, and a doctor is predicting the present. When we say, what we're saying here with causal inference is, whatever this object is that we're estimating, we're going to call it a causal effect. We're going to estimate this thing called a causal effect. It is useful to us if it guides the future. Meaning, like, you know, I estimate I estimate the effectiveness of a vaccine. Okay. I estimate a smallpox vaccine's effect on, you know, smallpox mortality. All right. That's not in the future. That's like, you know, I give a bunch of people a vaccine. I give a bunch that didn't, or, you know, maybe it's like, I want to know the effect of aspirin on, well, I guess all these things kind of do have temporal things. But my point here is that you estimate the causal effect, right? You estimate the causal effect. But why is it useful? It's useful because you're probably going to want to know if you should give people a smallpox vaccine, or you're wanting to tell people you should or shouldn't take this medicine. Okay. So to the degree that it kind of like it's capturing something real, you get to kind of depend on it a lot of the time. All right. So they all kind of have like, you know, they all kind of have like future, present, past kind of orientations to them, but it's more about what you're going to use them for than anything. That are you going to use them to inform what happens when you do something, or are you going to use them to inform what's going to happen even if you don't do something? Okay. Yeah. And Jeff brings up a good point, you know, which is that these fictional things, you know, you have to kind of remember George Box was a statistician, and he said all models are wrong, but some are useful. And so a lot of what we're going to talk about is kind of in that frame. So like a lot of when I say things like fictional quantities, I want you just to kind of remember the goal here, big picture, is not to describe reality. It's not to come up with a grand theory of like, you know, the deep, deep nature of reality. That would be like causality kind of things. Ours is a lot, in some ways, simpler. Okay. I want to know the causal effect of the minimum wage on employment because I want to know if we should continue to use minimum wages. That's it. I want to know whether or not it was beneficial to do it or not. Nicholas says, I'm having trouble understanding counterfactuals in relation. We're going to do that now. We're going to do that. We're going to do that later, Nicholas, and tomorrow when we get into colliders and confounders. Right now, we haven't started anything. Okay. It's not a different concept, but I'll explain more as we get to it. How does this differ from knowing the most influential features in a regression? Well, what we are doing right now, Ollie, is when we're working with causal inference, okay, it's going to be without reference to a regression. It's going to be without reference to any kind of theoretical modeling. All right. So it's going to be a particular kind of object that we can estimate with a regression, but not necessarily. And that's what I was trying to say here, which is, there are things that you do with regression where it's just prediction. And there's things that we're going to show over here where that regression sometimes is causal, sometimes it's prediction, sometimes it's causal. And we're trying to figure out which is which. Okay. Okay. All right. Keep those questions coming and I'll try to answer them as we go. All right. So let's kind of live in this world outside of regressions. We're not covering regressions till tomorrow. All right. We're not covering any regressions until tomorrow. So right now, just kind of pretend that you don't know what one is. Okay. Let's start at the most basic ideas. And this is what I'm going to call like a naive approach to causal inference. Imagine these aliens come from outer space. They come to Earth during the COVID epidemic, and they're looking at these hospitals where or looking in the population, or really even looking in the hospitals, and they can detect in the population who got this disease. They can tell by looking at everybody, they group it together, and they say, all of these people have a disease, but this group of people that is on this machine, the ventilator, which looks very invasive, okay, it's got a thing going down their throat. This group of people that's on a ventilator is dying much more often than this group of people over here that's not on a ventilator. And so they draw the conclusion that the doctors are killing people with that ventilator machine. And the reason they draw that conclusion is maybe they ran a regression. Maybe they said mortality regressed onto a dummy variable equal to being on a ventilator. Or they just simply took an average mortality rate for people on ventilators, an average mortality rate for people not on ventilators, and they found that people on ventilators died more often. So they decide to come to Earth with a bunch of ray guns and capture the doctors and slowly take out those ventilators to save these people. And they're like, you're free. And they just notice that the mortality gets even worse for those people, and they're confused. We know, everybody on this call knows that that the people on ventilators die more often than the people not on ventilators, because the whole reason they're on the ventilators is because they're about to die, right? The whole reason that they're on the ventilator is that they are facing severe mortality risks, right? The aliens, for some reason, don't know that. The aliens do not know how the world works. And so since they don't have any common sense about the world, there's a lot of latent knowledge about cause and effect that all of us on this call have, and we're not even sure who taught it to us. I have no idea where I learned that sick people go to hospitals. I didn't know. I don't remember learning that. I know it though, right? And so the problem is common sense approaches to causal inference are absolutely great for navigating, like your own personal life. You typically rely on a lot of common sense causal inference. You make a lot of errors though, too. You make a ton of errors with common sense causal inference, but we use it all the time. But in research types of contexts, you can't use common sense causal inference, because the whole reason that you're studying something in science or industry or whatever, the whole reason you're studying it is because there is no common sense. Nobody knows what this relationship is. Nobody knows the magnitude. Okay? That's why you're working on it. If you already knew it, if everybody already knew that, you wouldn't do it. Nobody's doing RCTs on the effect of ventilators on mortality. It's well known. Okay? So this is the thing I want you to leave you with, is that, part of the problem sometimes is this issue of this issue of causality really is not something that you theoretically kind of know a lot about a priori. And so it's really easy to make these mistakes. And so let me tell you 3 ways that these mistakes can get made. Number one, this is the thing too. The stats community has somehow made this phrase, call it causation is not correlation is not causality. They have been really successful. That's kind of a phrase that I bet even my kids in high school have heard that phrase. You know, that phrase has been so popular that everybody kind of knows that you can't just look at a correlation between things, a regression. Can't really look at a correlation between things and necessarily deduce that one thing causes another. But I want to actually go a little deeper than that. Okay. Causality concepts actually do not require more than one person to think about. Okay, so like Jeff and I, know each other. Jeff Swigert, who was on the Day One channel, we know each other. And Jeff has got a doctorate in economics, and he might wonder to himself, I wonder what the causal effect of this PhD in economics has been on my wages. I wonder what it was. Okay. Versus, or this one right here. If a doctor puts a patient on a ventilator, will her COVID symptoms improve? One person. Causal questions can be expressed in terms of one person. Correlation questions cannot be expressed in terms of one person. You cannot do it. You have to have numerous people in order to calculate a covariance. You have to have numerous people in order to calculate a variance. You have to have columns of data, not a cell of data. So already what we kind of see is that there's something statistical about a correlation, and there's something kind of non-statistical about a causal question. And, we kind of do understand that at a level, even if we don't know exactly what to do with that. Okay. No, Chang says maybe causality is one thing leads to another, but here, I'll put this up here. Chang said maybe causality is more like one thing leads to another, but regression is correlated. Causality is about one thing causes another, and regressions are when the goal of a regression is to estimate a causal effect. Regressions are trying to estimate that causal effect. Okay. All right. So we're going to keep unpacking it. I can tell that this is something we're going to need to get to fast. So first thing is correlation doesn't mean causality. Second thing is Chang said one thing leads to another. You have to be careful with that phrase, leads to. Okay. Coming first in a sequence of events does not necessarily mean the first thing caused the second thing. It's a logical fallacy to draw that deduction solely based on the sequence of events. Okay, it's called post hoc ergo propter hoc. It's Latin, describes a fallacy. It's called after this. So this thing happened second, therefore it was caused by the first thing. Okay, so every morning the rooster crows. Every morning the rooster crows, and then 30 minutes later the sun rises. Did the rooster cause the sun to rise, or did the sun cause the rooster to crow? Yeah, exactly. Jeff brings up, you can see in Day One, Jeff says sequence of event causality in econometrics is called Granger causality. Which is different than what we're talking about. Okay. So what if the cat had killed the rooster? If the cat had killed the rooster, it would have almost positive it's not going to cause the sun to not rise. Okay. So just because two things happen in order, one thing happens before, depends on what leads to means, doesn't mean that the first thing caused the second, even though they may be correlated. Okay. And then third, sometimes things are not correlated and there is a causal relationship. So I asked, some of you know how to pilot a sailboat. I'm going to go ahead and just tell you right now, I've never been on a sailboat. I asked my friend Seth Hain to draw a picture I had in my mind. He's never been on a sailboat. So I get it. This is a metaphor and not how actual sailboats work, but I still like the metaphor. So here's a woman piloting a sailboat across a windy lake. Okay. And sometimes she moves the rudder here, and sometimes she moves the rudder there. She moves it some direction perfectly, whatever that means. She's perfectly moving the rudder. What does perfectly mean? She moves the rudder back and forth, and in fact, she never changes her coordinates. She is always pointed in the exact same direction. Okay? So compare that. Imagine instead of moving the rudder back and forth for the reasons that she is doing it, instead she rolled 2 dice. 1-1 puts you at the, top left part, puts you right there. And all the way down to 6-6 puts you there. Okay? Puts you there. And so here's what happens. She rolls a 1-1, she puts it there. She rolls a 1-3, she puts it there. She rolls a 2-5, she puts it there. 3-8, she puts it there. She just moves it around. She's moving she's moving the rudder in both of those scenarios. Okay? So scenario 1, she's moving the rudder in response to the wind and waves in order to stay on course. Scenario 2, she's also moving the rudder in response to the random dice. Okay? Both situations involve her moving the rudder. But scenario 1 shows no correlation between the movement of the rudder and her coordinates, but scenario 2 will create a zigzagging across the lake. And what we want to understand, so all we're trying to say right now, the purpose of this right now is just to say that just because there is no correlation does not mean there is no hidden underlying causal effects. Human beings distort correlations. The more rational, the better their policy, the better their choices are with respect to some objective. So in this case right here, in the United States, we have something called the Federal Reserve. The Federal Reserve is the United States central bank. And when a recession is forming, they will enter into open market operations and buy bonds with cash that puts more money into the economy. And in our economic models, if you do it correctly, the buying of bonds will stop the recession. and you won't find any correlation between buying the bonds and GDP. And yet, had they just randomly bought bonds, there would be an effect. And if the models are right, assuming our theory of monetary policy is right. Okay. So that's kind of what we're trying to say here is that, be careful about over relying on regressions or simple differences in averages or, elastic nets or neural nets or any kind of like method that's just simply trying to look at the association between two variables or multiple variables. Okay, you got to be careful with it because it's not always the case that the correlation or the lack thereof means a causal effect. And so what we're trying to figure out, well, when does it? When is it that I can interpret when two things are moving together or not as a causal effect, and when can I not? All right. So it's kind of been coming up when people are talking about regressions. It's kind of coming up that we're so used to thinking about causality in the context of a statistical model. And the biggest one is ordinary least squares. In fact, ordinary least squares is probably the single most, get outside of the randomized control trial, the running regressions with covariates is the single most common way that people, in the quantitative fields think of causality. They think of it almost exclusively in terms of a statistical model. They'll do something like this. They'll go, yeah, I know what causality is. It's this. Huh. They'll go, that's causal. Okay. They'll say that's causal. And what they're saying is when this changes, it quote causes that to change. Prediction is more like this. That's prediction. Prediction is like estimate those parameters, fit them to the data, get predictions. So like prediction is more about this stuff and causality is more about this stuff. Okay. But you don't always get to interpret this as a causal effect. Sometimes it is, sometimes it isn't. And so what we're wanting to do is before we ever even go to a model, we need a definition of a causal effect. Okay. We need a definition of a causal effect, and that's going to require some concepts that many of you haven't heard before. All right. So just stay with me. We're going to have to introduce some notation. Right. So the first thing that you're wanting to do in a causal study, not in a prediction study, not in a descriptive study, but in a causal study. What is the causal effect of an advertising campaign on sales? What is the causal effect of Medicare on mortality? What is the causal effect of prices on quantity demanded? Okay. Those are research questions. Okay. Those are research questions. That might be your project. Your project is studying the effect of small classrooms on student test scores. But what you've got to do is you've got to turn in a causal study, you have to turn your research question, which can be expressed as a sentence, into a specific aggregate causal parameter. That is the first step. And I've got to show you what is a causal parameter. All right, but that's our first step. We have to turn a research question into an aggregate causal parameter. Once you have decided what your parameter is associated with your project, your project could have many different, completely reasonable, causal parameters. There won't be just one. So you have to make a decision about which one you want. Second, you have to decide what are the things that you need to believe in order for that parameter, that causal parameter, to be obtained with data. Still, we are not estimating it. We are just making statements about the kinds of things that would have to be true in order for us to use our data set to get an estimate. And then the last is the estimator. The last step of a causal study is to build out a model that uses your data and uses your beliefs from the second step and gets an estimate of that aggregate causal parameter. An estimate. An estimate is not the same thing as the aggregate parameter, as we're going to see. It's a guess. It's a guess. You go to the fair, there's a big jar of jelly beans, and they're black and they're white, and you have to guess at how many black jelly beans there are in the jar. Okay? The truth is like the aggregate causal parameter. The guess is the estimate. And so the assumptions are things like, well, if each, it's like the assumptions, well, in my example here with the jelly beans, it doesn't exactly work, but it might be, there might be something you could do. You could do something. But anyway, the point here is that the guess and the actual truth are different things. And what makes causality a little bit different is it's not like a blind guess, right? You're not just running a model. You're not just running a regression. You're saying, well, if these things are true, then that model will get it right. That model will be right on average. And if these things are not true, then that model won't be right, even though I used the model. So what most of us do is we skip that step. Maybe we skip this step even. Maybe we even skip this step. And we just go right to what? Running regressions. We go right to running regressions, and we just hope and pray that whatever number that we care about when we run that model, we just pray that it's equal to a causal parameter. That is how errors are made. Skipping these steps is the source of major errors. Okay? All right, so let me tell you the history of this, and then we're going to get into some actual math. Okay? So there's three new ideas. There's three new ideas that not everyone probably has heard all these ideas. Some of you have heard one of them, but not necessarily all of them. Okay? The first idea is this idea called the counterfactual. It's called the counterfactual. Philosophers came up with it, and it's very central in causal inference. But this idea of the counterfactual is what makes causal inference hard. And the wide agreement amongst the philosophers to think about causality in terms of counterfactuals basically almost killed the entire causal inference project before it ever got really started. Okay, so we need to figure out why that would be. Why is it that counterfactuals would be so valuable and so deadly at the exact same time for causal inference? Second is we're going to use a phrase called treatment assignment mechanism. All right, treatment assignment mechanism, which means that we're going to learn what treatment means. We're going to talk about treatments being assigned to people, places, or things, and we're going to talk about mechanisms that do that assignment, of which there's lots of different mechanisms that can assign a policy to a city or assign a medicine to a person. There's lots of different ways you could do it. Okay. And Jerzy Neiman and Ronald Fisher are going to be the people we're about to focus on. And we're going to talk about the modern randomized controlled trial. Okay. And then last is something that you're going to hear me say over these 4 days. There is no such thing as the causal effect. There is many causal effects, and you have to pick a parameter that summarizes them in the way that you want them summarized, which means that some of the causal inference that we're going to be discussing is actually non-trivially different from the stuff we learn in our regression classes, which sort of do talk in terms of one causal effect. So let me see where we are. Yeah, Miguel, I'm going to do it in just a minute. I'm going to do it in just a minute. I mean assumptions that you have to make in order for a correlation to have an interpretation as a causal effect. It's a certain kind of belief. Like in a differences in differences, it would be parallel trends. In an RCT, it would be the independence assumption. And with a regression model, it would be that exogeneity assumption. These are the beliefs that you have to make about the data in order to justify the model. Pedro, it's not really, that's a good question, Pedro. It's actually not a belief in the literature. It's not a belief in the literature. It's a belief about your data set. It's a belief about the treatment assignment mechanism. Nothing about the literature will answer that question for you. Nothing about that literature is going to answer the question for you, because as we're going to see, there are situations where a treatment assignment mechanism in one place is done a certain way, and in another place it's done differently. Okay? In a randomized control trial, you have a set of beliefs about the way in which the treatment is assigned that is different from what happens outside of the lab. Okay, so we're gonna get into that. So don't think of it as beliefs that you would read in a book. It's not going to be that kind of beliefs. All right, it's going to be mainly the beliefs surrounding the generation of your data set, not the theory of the phenomenon. Okay. Okay. So here's modern philosophers. Modern philosophers are the ones that introduce these counterfactual comparisons. I think it goes back to David Hume, the Scottish philosopher, and who's a contemporary of Adam Smith. He was a little bit older. They were close friends, but it's not him. He's one of the main sources of this, but I have two other quotes that I'm going to put. So this is John Stuart Mill. He's a 19th century moral philosopher and an economist. Here's what he said. This is his theory of causality, but it's also his theory of causal inference. Okay, because he basically says people would be apt to say. I'll explain this once, reading it, and then I'll go back and explain it. Okay. If a person eats of a particular dish and dies in consequence, that is, would not have died if he had not eaten it, people would be apt to say that eating of that dish was the source of his death. All right, let me rephrase it. If a person eats a pizza and then they die, that is, they would not have died had they not eaten that pizza. Then people would conclude that the pizza caused the death. Okay? David Lewis is a late 20th century metaphysical philosopher. He's the second greatest metaphysical philosopher after Ludwig Wittgenstein. He writes this. He says, causation is something that makes a difference, and the difference it makes must be a difference from what would have happened without it. All right. So what did we just read? Both philosophers say that our beliefs about cause and effect require comparing what did happen when someone did something to what would have happened had they not done that thing. Okay? That's sort of the this like definition that they're coming up with. Okay. Luvo says, when it comes to assumptions and belief, is it not the model you are planning to use that drives those beliefs and assumptions about the data? No, not in the design tradition, Luvo. We're going to get into that in a minute. We're going to get into that in a minute, but the answer is no. It is not the model that drives the beliefs. It's the beliefs and the assumptions that choose the model. Okay? The beliefs, oh, wait, here we go. Yeah, no. So it's the other way around in this design tradition. It is your beliefs and assumptions about the data that causes you to pick one model over another. Some models work with some beliefs, some models work with others. Okay? So you can never, the problem in causal inference is really never the model. The problem is probably that you used the wrong model that did not really fit the data that you were using, because the data was created in a way that is not consistent with that model's assumptions. Okay. So counterfactuals, I said, almost derailed causal inference just as it got started. Inside both of those definitions, you have them talking about beliefs. Look, if a person eats a pizza and then they die, that is, they would not have died had they not eaten the pizza. There's those two comparisons. Two different events happen. Two different outcomes happen. If they're not the same, then what does John Stuart Mill say? He says, well, then it would be reasonable to believe, to infer that the pizza caused the death. So here he's got like this metaphysical part, and here he's got this belief part. Here's the causal inference based on some thought experiment that's being done. Okay. And by defining causal effects in that way, where John Stuart Mill says you've got to have two things at the same time, Mill says to know a causal effect, you need two data points for the same person at the same point in time. Number one, death if he eats pizza at 10:40 a.m. Central Standard Time, and death outcome if he eats pizza at 10:40 a.m. Central Standard Time. Well, he can eat pizza at 10:40 a.m. and not at 10:30 a.m., but that is not what Mill is saying. Mill and Lewis are saying that they think philosophically you should define a causal effect for as a difference in outcomes at the same point in time for the same person, for the same unit in two states of the world. One where the event happened versus one where it did not. And the reason I say that causal inference nearly derailed, the reason why I say counterfactuals nearly derailed causal inference is that if you need both of these to know a causal effect, but it is literally impossible to know both of those, then, and here was the bad news, it is impossible to know a causal effect. That was the implication. That was the implication of this definition. And see, when Mill's 1 and 2 points are positive. Positive? What do you mean, Chris? What's that mean? positive?
You say both of them. Read your points very well. You say if he eats pizza. I think you wanted to say if he did not on the second
Oh,
one.
sorry. Thank you. Thank you, Chris. Chris is dead right. Yep. If he does not eat pizza. Thank you. Exactly. Right. So Mill says, I got to know if he's going to be dead when he ate at 10:40 a.m. or I got to know if he's going to die when he ate the pizza at 10:40. And I got to know if he's going to die if he didn't eat the pizza at 10:40. And then I got to compare it. And then I got to compare it. And you can't compare that because whichever thing he decides to do, if he decides to eat the pizza, at 10:40, then that doesn't exist. Or if he decides to not eat the pizza at 10:40, then that one stops existing. Whatever choice he makes immediately eliminates the other thing. And once it's eliminated, since Mill and Lewis and many others agreed, it was like a collective agreement, since they all kind of agreed that that's the only reasonable definition of a causal effect, and in the where the source of knowledge would be, they basically both defined it, which was really valuable, and they made it impossible to measure it. Two things. The good news, a great definition of a causal effect, because it really seems undeniable that that must be what causality is. Bad news. Impossible now to calculate it because of missing counterfactuals. So it was like good. I got good news. I got bad news. The good news, what's the good news? The good news is that's the best definition of a causal effect that anyone has ever heard. What's the bad news? Now you have destroyed my ability to ever measure or calculate a causal effect. Okay. Until 1923, it was last year. I think I knew that. I think I knew that it was 1920. I think I knew last year it was the 100-year anniversary, but I don't think I wonder if I think that crossed my mind. Anyway, so that changes. 1923. This is from Don Rubin, a 1990 article he wrote. This is what he says is the statistical origins of causal inference. He says, yet, although the seeds of the idea that causal effects are comparisons of potential outcomes can be traced back at least to the 18th century, I think he means David Hume, the mathematical notation, the formal notation for what we're going to call, or what is called, potential outcomes, the formal notation for that thing that Mill was talking about is not invented until a master's thesis by a Polish graduate student named Jerzy Niemann, which ends up being a seminal article in causal inference. Foundational, cannot be overstated how important it is. Okay? So we're going to now take a break. We'll come right back. And when we come back, we'll look at Jerzy Niemann, and we're going to get now into the potential outcomes model. We're going to start getting into the potential outcomes model. So we'll be right back. Okay, so I know we're going slow, but here's why we're going slow is it's going to speed up once we get into the estimators. The reason we go slow is because this potential outcomes model, as it's already kind of like showing up a little bit in the Discord and elsewhere, is that there's a lot of awkwardness that I think people typically have when they're kind of going from everything they do know, and then they're, wanting to map everything new onto everything they already know. And we have to kind of do that on the back end. But then the other thing is the potential outcomes framework that we're about to learn is very deep and very subtle. Okay. And it's got ideas that we've already discussed, but everything we've discussed right now is kind of more like fictiony and stuff like that. It's when you actually work with the notation that it gets really, it really starts to show you what you do and do not understand. Okay. So we're going to start now. So this Jerzy Neiman master's thesis, 1923, where he describes a field experiment. And he's describing in the field experiment, basically something like this. He's like, imagine that you have like a huge number of gardens, okay? And each of these gardens has different kinds of soil, all right? It's got different kinds of soil, and you're wanting, and they're all growing the same kind of vegetables, but they have different kinds of soil. And not only that, you've got different kinds of fertilizer that you can put on this soil, right? Now, so you've got this input fertilizer, of which there are different varieties, okay? And you've got output, which is going to be the yield associated with each garden and all possible different fertilizers. Okay, because there's like a bunch of different fertilizers, and there's a bunch of different fertilizers. And so the question is like, I could right here, for this one, this is like number 2, and this is number 3, this is number 4, this is number 5, it's number 6, 7, 8. All right, so there's like 8 gardens. And maybe there's like 100 different fertilizers, right? 100 different kind of fertilizers, which means I could put on garden 1 up to as many 100 different fertilizers, right? I don't know which one I'm going to do, but I could do any of them. Okay. So he introduces this notation right here. He says UIK is going to be the yield of the ith variety on the kth plot. So this is like, this right here would be k equal 1, right? This would be like k equal 2 and so on, right? So you've got different plots of land. We index them with the letter K, and you've got different fertilizers here, and we'll index them with an I. Okay, we'll index them with an I. Right, so you got different ones of each. Depending on which plot of land we're talking about, and depending on which fertilizer is applied to that particular plot of land, there is a whole range of potential yields. Potential yields that could happen. So I could be working with this square garden, and I could use fertilizer 1, I could use fertilizer 2, I could use fertilizer 3, and associated with each of those fertilizers is an outcome for the garden. Okay? It's an outcome for the garden. But this UIK is describing all possible or potential garden outcomes associated with each different fertilizer, I. Okay? But the farmer cannot apply all fertilizers to a single plot of land, at least not at the same time. Okay? Can't do it at the same time. She can only apply one fertilizer at one point in time. So it would be like this. It would be like this. Okay, so I've got like here, right? And this is like, oh, dang it. Keep doing the wrong thing. So this would be like I, okay? This would be like all possible fertilizers. Okay, this is all possible fertilizer varieties. I'll call it V, right? And then this is going to be like UIK. We'll call that like, K, right? And maybe what there is like, a huge range of possible outcomes, right? There's a huge range of possible outcomes with mass, whatever, right? It doesn't have to be curved like that, but let's just say it is like that. But once this farmer decide, whoa, where'd that come from? Once it decides on which fertilizer it's going to use, the rest of the possible like potential yields disappear. So once the specific fertilizer is chosen and therefore assigned to the K plot, all other potential yields vanish. Okay. All other potential yields vanish, leaving only the one potential yield associated with that specific treatment assignment. What we call it, treatment assignment or fertilizer variety chosen. Okay. Now, this was like the first time anybody had ever written down this idea of what John Stuart Mill was talking about. John Stuart Mill was talking about, he was talking about that. He was saying, well, there's all these different outcomes associated with all these different choices, but you can't observe all of them and you don't know what all of them are. You just know the one that you chose. Okay. But if you want to know the effect of the fertilizer on the outcome, you got to have something to compare it to. And whatever you're going to compare it to, doesn't exist anymore or never, it's gone. It was real, but it's gone. So he says for each fertilizer, there is an associated potential yield. He collapses it into this one, vector, which he considers to be a priori fixed but unknown. Meaning, and what does he mean? He means it's fixed and meaning that this is not changing. It's not changing. Nothing's going to make it change, but nobody knows what it is. Okay? Nobody knows what it is. But so it exists because if you had made a different choice, you would have gotten a different outcome, possibly. But, nobody knows what that range of stuff is. So it's a priori fixed, but unknown. Then Niemann writes down some kind of classical statistical model called the classic EARN model. And he says the farmer's going to go from garden to garden, right? It's going to go from garden to garden. And as he goes from garden to garden, he's going to reach inside an urn and pull out a fertilizer. And then he's going to put that fertilizer here. And he's going to, it's going to be sampling with the replacement. So he's going to take it out. He's going to put it on the garden. He's going to go to the next one. He's going to take it out. He's going to put it on the garden. And he's going to do that to all of these gardens. Okay. So there's two things that he's doing in this paper, this thesis. There's two things he's doing. First, he introduces potential outcomes notation, UIK. Second, he introduces a method by which the farmer assigns the fertilizer, or what we're going to call treatment assignment mechanism. And the treatment assignment mechanism that he uses is the bingo ball machine or classic EARN, or what we call randomization. That's what he does. It is not known, Chris. Not exactly. We'll see in a second. Okay. It's not exactly. It can be, we'll get into that in a minute. So he introduces randomization. People draw fertilizer from an urn like a bingo ball machine with a replacement. They apply it to each square garden. Fertilizer moves us from all possible outcomes to the realized outcome. What's that? This is all possible outcomes right here. UIK. UIK is potential outcomes. Okay, it's potential outcomes. And this right here is U bar, I equal I star K. And that's called the realized outcome. The difference between the potential outcomes and the realized outcomes is that the potential outcomes are not known. They are unknown because you don't know all of these. You don't really know any of them actually until you make a choice. And when you make a choice, you will observe 1 point from the distribution and only 1 point. And that 1 point is called the realized outcome. All right. His thought experiment, that classic urn model, that's how they used to kind of motivate various kinds of randomizing devices. Neimann's urn model was a classic thought experiment, but it was stochastically identical to the RCT. His arch rival, Ronald Fisher, writes a book 2 years later, kind of like the mixtape or mostly harmless econometrics, in that it's called statistical manual for research workers or something like that. I've forgotten the exact name. And 2 years later, 1925, he's got a footnote in which he calls for randomization as the basis for causal inference. Now, he doesn't use that exact phrase, but he basically argues that it's not enough to have a treatment group and a control group. You've got to randomize the treatment. All right. And that was the innovation. 1923, 1925. They come to it independently. That was the innovation. The treatment assignment mechanism. No, he didn't. But he didn't because Neiman was just a master's student. The master's thesis was written in Polish. It was not translated into English until 1990. And Fisher appears to get to it independently because you can see in some of his earlier writings from like 1918, he's talking in this way, but without any notation. So he's kind of talking back in 1918 using potential outcomes. He doesn't call it that, but potential outcomes. He uses it in context of talking about height and eating food and stuff like that. But then the randomization as the treatment assignment mechanism, I don't think you can find it until his writings in 1925. But he seems to independently come to the same conclusion. They don't ultimately, when they do meet, they hate each other. They despise each other. Neiman becomes a professor at Berkeley, UC Berkeley, where he spent most of his career. Fisher, I'm not exactly sure where Fisher was. He was in London, but that's where it was. Seth says, what do I mean? It's stochastically identical. It's identical in the sense of he's describing a randomized control trial. He's describing, essentially a randomized control trial. Yes. Okay. Great thing. Let's just do this, Sebastian. Let's look at this together. Maybe I need to update my thing here. It's taking forever. So let's do this. Let's go here. Okay. So let's go UIK. Right? Nice. I would go like this. fertilizer type potential yield, UIK, right? And this will be I. Okay, we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10th variety. And we've got different yields associated with each variety. So like if you use the first fertilizer, you'll grow, 20 carrots. If you use the second one, you'll grow 25 carrots. If you use the third one, you grow 5. If you use the fourth, you won't grow any. If you do the fifth, you'll grow 100. If you use the sixth, 75, 25 again, 30, 50, 40. Okay. But so this is the full distribution of all possible or potential outcomes. Each outcome is associated with a particular treatment. Okay. That's what we want to say. It's like each fertilizer type is associated with a particular potential yield or potential outcome. Okay, UIK. Assume that the farmer chose I equal 2. If the farmer chooses I equal 2, then the realized outcome will be 25. It'll be U 25. It won't be, it'll be like, I called it bar, but like, it could be like star, it could be whatever. It's just basically a particular value. It is no longer a vector. It is a particular value equal to 25. So it's like this happens. The others are gone. And that's the only thing that happens. And that becomes the realized outcome. Does that make sense, Sebastian? Does everybody understand that? The movement between the potential outcomes and the realized outcomes? Yeah, you could, but we could say, yeah, HB, you're supposed to describe all, you're supposed to just, how do I zoom? You're supposed to describe really everything. So you could do this. Yeah, you could go, you could do that. You could say you want to. You could say, no fertilizer. And maybe that's, 1. It's fine. It could be whatever. The point here is that there's all these different types. There's all these different things that you could do. Okay. And this is all of them. And associated with each of them is a possible outcome, potential outcome. Yes, exactly. So is it because we chose the number 2? Exactly. We chose number 2. Right? Now we haven't said, so this is the realized outcome is the potential outcome associated with a particular treatment assignment. But the classic earn that he described was a mechanism that chose I equal 2. And in that, it was a randomizing device. So you have to keep separate potential outcomes notation with the mechanism by which the treatment is assigned. They're different. Okay. K is the name of the garden right here. Garden 1, garden 2, garden 3, garden 4, garden 5. So in this kind of thing right here, we were kind of working with one particular garden. I just was using that UIK notation, but no, we're not, Mara. We're not assuming the properties of the land are the same. That is kind of the, so the potential outcome, that's a really good question. That's a really good comment. So we are not assuming that the properties of the square of each K garden are the same. One of the things that makes potential outcomes notation unique is that we actually do not bound anything, any of the treatment effects or the people or the units. It's called unbounded heterogeneity. We basically set, we commit up front to not knowing that potential outcome, those potential outcomes. We don't know. We don't know if they're the same for each person. We don't know if they're almost the same. We don't know if they are radically different per person, per garden, person, per fertilizer treatment, so we kind of upfront just say, don't know. They're fixed, they're real, but I don't know what they are. I only know what happens. The only thing that you ever know is what happened when you made the choice. So Jeff Swigert that I was talking about earlier, Jeff does not know what his wages would have been under every possible choice that he could have made after he graduated from college. He doesn't know. All right. He could have gone and got a different doctorate. He could have not gotten a doctorate. He could have moved to a location. He has no idea. He just knows his wages right now. That's all he knows. He knows his wages right now, and that's it. So, Hito Embens and Don Rubin in their 2015 book, which I think I have here, he says, they talk about this treatment assignment mechanism, and they say, and I actually don't know where that phrase originates, but it's now commonly called treatment assignment mechanism. All right. Cherise, you and Morrow basically asked the same question, by the way. So treatment assignment mechanism, Embens and Rubin in their book, they say, before the 20th century, there appears to have been only limited awareness of the concept of assignment mechanism, not randomization, assignment mechanisms. Okay. But we've been using treatment and control experiments forever. Even in antiquity, they were using it. Da Vinci did experiments. Da Vinci did not randomize anything. Okay. That was the key thing. People started to become aware that different assignment mechanisms would choose different realized outcomes from that distribution. And very little awareness of that exists prior to Neiman and Fisher. Okay. In the 1930s, though, randomized experiments became firmly established in some areas of scientific investigation, notably the agricultural experiments. Okay. But there was no formal statement for a general assignment mechanism, and moreover, not even formal arguments in favor of randomization until Fisher 1925. Okay. All right. So econometrics as a field, all right, it did not use potential outcomes. It did not use potential outcomes. It did briefly. At the very beginning of econometrics, the very first Nobel laureate, Tinbergen was the first Nobel laureate in economics, I think with Frisch, and he used potential outcomes. This guy named Roy in the 50s, he used potential outcomes. There were a few random people. Quant uses potential outcomes, but pretty much 99.9% of the people that came after that did not use the potential outcomes to talk about causality. They instead used only the realized outcomes. So what I want to do is I want to show you a video real quick. Let me just double check my audio is working right. Okay, I got to do it in the same system. All right, so Let me show you this video. This is a interview I did with Hito Embens, who won the Nobel Prize in 2021. Okay, so let me pull this up. So Hito Embens, professor of economics at Stanford University, wins the Nobel Prize in economics in 2021 with David Card and Josh Angerson. This is him talking about potential outcomes as a theory of causality in econometrics versus the realized outcomes and why he thinks one was superior to another.
Later, sort of around that, well, a little later, but sort of influenced by that, I wrote this book review of Henry's book on kind of with econometrics readings, where I looked back at Timberger's work, where for the supply and demand for the simultaneous equations setup, he starts off being very clear in terms of the potential outcomes in a way that still resonates a lot with me. And it's kind of interesting to see how the econometricians then generalize that kind of to these simultaneous equations models with K endogenous variables and M exogenous ones, but doing it purely in terms of the realized outcomes.
Right.
And that, I think at that point, a lot of the clarity was lost.
Yeah.
And we lost kind of the statistics part of the audience because it didn't really, it wasn't very clear what was meant anymore.
That reminds me,
I think the potential outcomes are a big part of made this super clear.
I want to hear it one more time, okay? Because it's only a minute. That was the first time. I want you to listen again, real close to what he's saying.
Later, sort of around that, well, a little later, but sort of influenced by that, I wrote this book review of Henry's book on kind of with econometrics readings, where I looked back at Timberger's work, where for the supply and demand for the simultaneous equations setup, he starts off being very clear in terms of the potential outcomes in a way that still resonates a lot with me. And it's kind of interesting to see how the econometricians then generalize that kind of to these simultaneous equations models with K endogenous variables and M exogenous ones, but doing it purely in terms of the realized outcomes.
Right.
And that, I think at that point, a lot of the clarity was lost.
Yeah.
And we lost kind of the statistics part of the audience because it didn't really, it wasn't very clear what was meant anymore.
That reminds me,
I think the potential outcomes are a big part of made this super clear.
So basically what Embens is saying, who by the way is just absolutely the most wonderful, one of the most wonderful.
So I think as speakers or
what was that? Wonderful people I've met in the profession. But the thing he seems to be talking about is that at the very beginning of econometrics, because they had no, I don't know why, but Tinbergen and others would talk about causality in terms of these kinds of comparisons, okay? But then the modeling would only be this. What is this? This is the bars. These are the bars that I'm talking about. You chose a particular fertilizer, 2, and you got a particular outcome, 25. And then they would like only use the realized outcomes to describe causality, which when they did that, when the econometricians, according to Embens, chose to adopt realized outcome notation to describe causal parameters, they departed from the statistics design tradition. And that's why he said they lost the statistics part of the room, meaning the statisticians just kind of, you know, they were no longer doing stuff that was particularly relevant in the eyes of statisticians. A lot of the work ends up being, you know, so rooted in economic theory and has very little to do, you know, very little value that anybody can see to anybody else. Okay. So what is the potential outcomes framework? So for the rest of the class, except for one moment, we're going to only be working with dummy variables. So when I did this right here, okay, when we did that, or we did this, okay, when we did, you know, this part right here, okay, so when we did this, we had a lot of different fertilizers, okay, and we had a lot of different potential outcomes. We're going to do something different now. We're going to say there's two types of fertilizers: no fertilizer or some particular value of fertilizer, and associated with each fertilizer type is a potential outcome. Okay. So we're going to stick with our ventilator example because that's how I wrote the slides up. So we're going to assume a binary variable called D, and D is going to be for a particular person. I is going to index an individual observation, like a garden. Here it's going to be a person. And T is going to be at a particular point in time. I'm not going to use T pretty much ever for the rest of the workshop because I just wanted to emphasize right now that you're either on the ventilator or you're not on the ventilator. So like everybody on the call right now at 11:33 a.m. Central Standard Time, they are not on a ventilator. But if you go down to the local hospitals in a big city anyway, somebody's on a ventilator. You can't be on the ventilator and not on the ventilator at the exact same point in time. And that's why I wanted to put a T here to really emphasize that this is an either or condition. Okay. Then you have potential outcomes. All right. It's a different variable for each fertilizer. Yeah, exactly. Well, it's a different variable. It's a particular kind of treatment of which there are multiple treatment statuses. Okay, so it's like the fertilizer. So this would be like ventilator, and this would be like not on the ventilator, on the ventilator, right? And then you have potential outcomes, and potential outcomes is like this right here. And you have, for each treatment assignment, you have a potential outcome. So for a given garden, if you choose for that garden a fertilizer equal to 0, meaning no fertilizer, then that garden's going to grow 5 carrots. But if you choose a fertilizer of equal to 1, meaning like, you use a particular kind of fertilizer, it's like compost or something, then you'll have a 20 carrots. Okay. You can't have both of them because you can't do both of those, but they both exist, or they're both, a priori real, or they are a priori fixed, but unknown. Fixed is probably the better word. All right. So in our ventilator example, you would have, for person I, let's say Seth. Okay. Say Seth is person I, and it's right now. Seth can decide right now if he wants to be on a ventilator or not. All right. If he chooses to be on the ventilator, it's D1. We then look at his health in a world where he's on a ventilator, and that's what it is. Had Seth chosen to not be on the ventilator, there'd be some health associated with that, and that would be his health if he's not on the ventilator. Now, Seth doesn't know what these are, but they're real. Like they're real. Why do you know that they're real? Because whichever choice he makes, it'll exist. One of those two will exist. That's what we mean by real. I'm not crazy about that word, but it's like it's gonna happen. One of those two will happen. So potential outcomes refers to that idea of the a priori fixed but unknown outcomes associated with different possible treatment assignments, not different, it's like different values of the treatment. So you've got like a particular treatment, fertilizer, of which it can take on different values, the different kinds of varieties. We've collapsed it into just 2, but we had 11, right? The realized outcome refers to the posterior and known outcome associated with a specific treatment assignment. So if he decides to give this garden a fertilizer, well, then he'll have done that, and that'll be the realized outcome, okay? So potential outcomes become realized outcomes through the treatment assignment, not the treatment assignment mechanism, but by the choice. There's different ways that choices can be done, though. You can randomize. You could choose the best thing that you think is best, choose the best fertilizer for each garden. There's all kinds of stuff you could do. The reason that you choose the fertilizer is different from which fertilizer you chose. The reason is the mechanism. The choice is the assignment, okay? So the treatment assignment mechanism is what drives the entire effort to identify causal effects. Some treatment assignment mechanisms make causal inference trivial, super easy. Something about the randomized experiment, for instance, makes causal inference extremely easy. You can always get the answer pretty much if you have a large enough data set. You can always get it, okay? Something about that randomization makes it easy, and something about other mechanisms by which treatments are assigned to units makes it increasingly difficult, might even make it impossible, okay? Which means modeling is not what comes first. Make the statement about what the parameter is, and that second step has everything to do with whether or not you believe the farmer used an urn and pulled randomly from an urn the fertilizer versus a farmer that like gets in the dirt and says, you know what would really be best? I read an article on this fertilizer. I'm going to use this fertilizer to put it on there. Both situations put fertilizer on the garden, but they do it for different reasons. And the different reasons that they put the fertilizer on the garden is what's going to make it easy or hard, if not impossible. Okay? So that's taken us about 2.5 hours to get to the definition of a causal effect. And I know that that's a long time, but I've done this 100 times, and you lose everybody if you don't go slow. So definition 1. What exactly is the definition of an individual treatment effect, an individual causal effect? The individual treatment effect, okay, we're going to represent it with a delta sub I. Delta sub I. Delta sub I is the individual treatment effect for a person. This will be the individual treatment effect for Seth, or the individual treatment effect for Morrow, or for Sebastian, or for Chris, or for Becky, right? Well, so what exactly does that mean? It would mean this is my potential health outcome if I was on a ventilator for Scott at a point in time. Yes. Yes, Seth. We're sort of saying we're collapsing fertilizer, though, into there's a different binary variable for each fertilizer variety. Yes. And we chose a particular variety, and we said just collapse it all to something simple and just say 0, 1. Okay. Tylenol. Do you take the Tylenol? No. Do you take 200 milligrams of Tylenol? That's a 1. So we're being really specific about what exactly we are defining as the treatment, okay? So here we've got, I'm on a ventilator. This is my COVID symptoms. For me, at a point in time, I'm not on a ventilator. I'm Scott Cunningham. This is my COVID symptoms if I'm not on the ventilator. If they are the same, okay, if my health is the same under both of those scenarios, then the delta terms is zero. Causal effect of the ventilator on my COVID symptoms is zero. Probably since I don't have COVID right now. If you put me on a ventilator, well, my COVID symptoms I wouldn't have any COVID symptoms because I don't have COVID, but my overall health might actually get worse. If you put me right now on a ventilator when I don't need to be on a ventilator, you might scrape my, trach or whatever. You might scrape something. I might get hurt. I might get injured in some way. It's entirely possible that if you put a healthy person on a ventilator, their health could be worse than if you had not put them on it, right? So you've got the possibility here, and this is what I think it came up earlier. We basically are starting out with the possibility that we don't know what these treatment effects are. We don't know what they are, and we are not requiring that they be the same for everybody. We're not requiring that they be the same for everybody, and they can be different for a person at a different point in time, okay? Then what we have is the switching equation. And the switching equation is how we move from potential outcomes to realized outcomes, okay? And the switching equation is what picks there. Switching equation is what takes from the distribution of potential outcomes and chooses just one of them. Chooses just one of them. Chooses, of all possibilities, it picks one of them. How does it do it? It does it through the treatment assignment, meaning, Seth is not on right now, almost positive, Seth is not on right now a ventilator. All right, so let's just put this in here. He's not on a ventilator, which makes that a 0. Well, a 0 times anything is equal to 0. And 1 minus 0 is equal to 1. Okay? So since Seth chose not to be on a ventilator, his health right now is equal to Y0. Even though you hypothetically never knew what that stuff was, it was unknown but fixed. It got transformed mathematically. These notations are different. It might seem like kind of a trivial extra step, but it's really important to keep this realized outcome notation different from this potential outcome notation, okay? Because we only define the causal effects by this stuff over here. Now, had Seth chosen today to be on a ventilator, that would be a 1, that would be a 1. Well, if that's a 1, 1 times y1 is y1. And if that's a 1 minus 1, well, that's a 0. And he eliminated, by choosing to be on the ventilator, he eliminated y0, the only thing I'm observing. When I observe, I'm always observing a realized outcome, but what that outcome is associated with, if he's on the treatment, is y1. And if he's not on the treatment, it's y0. Okay? And that's all you know. That's all I know. All I know with Seth is that he's not on the treatment, so I'm observing y0. I don't know what his y1 would have been. Okay? All right. The fundamental problem of causal inference is this. If if you define the treatment effect in terms of two potential outcomes, but the switching equation eliminates one of them, then you don't have enough data to make that calculation. And you're not going to solve that problem with more data. Because no matter how many data points you get, you will always be missing one of the data points that you need to measure an individual treatment effect. And that is called the fundamental problem of causal inference. I can't remember. I think it's Paul Holland. Yeah, exactly. Well, it depends. Yeah, I'm sort of, it's really like, in this example with the ventilators, it's like somebody's making the choice. But you're right, it's an assignment. And that's the correct term. It's an assignment. Everybody is getting assigned to a treatment. If they could be choosing it, I chose to go get a PhD. It could be assigned to them. Your parents made you get a PhD. You flipped a coin. Someone flipped a coin and you got a PhD. There's different, but they're all kind of assigned because those ones or zeros are going to get assigned in the data set. So if you need both of them to know the individual treatment effect, I didn't know how else to say it with certainty. Like a particular kind of knowledge would be like, a measuring ruler that would let you measure the actual treatment effect. If you need both of them to make that measurement, but you're missing one of the key data points that you need to do it, you can't do it. If you're using Mill's counterfactual framework, Neiman's counterfactual framework, potential outcomes framework to frame all this stuff, see, it's all coming from defining treatment effects in terms of potential outcomes. If you define the treatment effects in terms of the potential outcomes and the switching equation deletes one of the potential outcomes, then you can't measure it. Period. So the fundamental problem is deep and you cannot overcome it. It cannot be overcome in this potential outcomes framework. Do not believe someone who says they have overcome it. Okay? Causal inference. Yes, it is. Chris says in the RCT, is it randomization, the assignment? Yes. Yes. In the RCT. So like, say, Chris, in the RCT, we're doing a study, okay? We're doing a study, and we want to know the effect of small classrooms on first grader test scores. You got small classrooms and you got big ones, all right? There's a few different ways that you could put a kid in a small classroom. One way is a randomized experiment. And that will assign each kid to a small or large classroom according to randomization. Another way that you could put a kid in a small classroom is their parents insist on it, right? That's a different assignment mechanism, and it's definitely not random. It's definitely not random. Okay? So, the fundamental problem of causal inference is deep. It cannot be overcome because you will never know, Jeff will never know his wages had he not gotten a PhD. All right? And no one, even in a randomized experiment, a person who is assigned to the treatment will never know what their outcome would have been had they not been assigned to the treatment. The person in the randomized experiment who is given the vaccination, we know their outcome if they're vaccinated. You do not know their outcome had they not been vaccinated. Just keep that in mind. Which means, though, that causal inference is a missing data problem. You're missing that data. And we kind of do know ways of dealing with missing data. There's ways that you can impute missing data. But the data that we are imputing, is the missing counterfactuals. Okay? So let's look at some definitions that are built on top of that definition that we were talking about. We got this individual treatment effect, and it's a number. So that's something you want to think about right now. So you have to kind of quantify these things first. So assume that the individual treatment effect is a number. It's a number. It's a scalar. Well, I'll just call it a number, but it's a scalar. It's like, e.g., 20 carats. It's positive 15 carats, because that's what I think that is what we had here. So it's like, here is we have, delta I equals y1 minus y0 equals 20 minus 5, 15. Okay, so I'll put that there. All right, so I don't know that, see, because I'm only going to either have a 20 or a 5. So I'm not going to know it's a 15, but it's a number. If it's a number, you can average it. You can average numbers. I can get the average age of the people on the call. Okay, can't really get like average, you can't get like average. Well, I don't know. You can pretty much average. You can pretty much average can't average whatever. You can average these things. So if it's a number, you can average it. So I got here one particular, garden, but let's say that I have like K treatment effects. Okay. And I've got like, I got K gardens and I got K treatment effect. So it's like 1, 2, 3, 4, 5, 6. Let's say I got 6 different gardens, and I got the first one. Let's say it was like 100 carats. If you put it on the fertilizer, it would cause 100 more carrots to grow. Let's say that one was a 15. Let's say that one was a 30. Let's say that one was a negative 5. That one's a 0. And that one's an 11. Okay. You can get the average treatment effect. And all that the average treatment effect is the average over all of the gardens. It's one number over all the gardens. Now, nobody actually has a 25. This guy has 100. That's not a 25. That's a 15, 30, negative 5, 0, 11. Nobody actually has a individual treatment effect equal to 25.17. But this is a summary of the individual treatment effects. Average treatment effect is simply a summary of everybody's treatment effects. And it's the mean. It's all that it is, okay? It's just the mean of everybody's. So this is what I meant earlier when I said that you have to decide on an aggregate causal parameter up front. And this would be an example of an aggregate causal parameter, the average treatment effect. And it's one of the most common aggregate causal parameters, the ATE. Okay? So aggregate parameters are based on individual treatment effects. They are summaries of those individual treatment effects. And there's different ways to summarize them. You could take the median, median treatment effect equal median 13. Just another way to summarize it. Okay? Yep, I will, Yuki. I'm going to do it right now. Here's the ATT. Okay, here's the ATT. So you've got a group of people that get fertilizer, 1, and you got a group of people that didn't. All right? You got a group of people that didn't. We'll look at a spreadsheet where we look at it. So you've got a group of people that get assigned to the treatment. Okay? Group of people that get assigned to the treatment. So maybe it's like this. Which type? So let's say that the first people did not get put on the fertilizer, And these people did. Okay. So you could say to yourself, well, see, even though they didn't get put on the fertilizer, that's not where the treatment effect comes from. Remember, the treatment effect is always about a comparison of two states of the world, not the realized outcome, but the potential outcome. So even though they were not put on the fertilizer, there is a treatment effect for them, which is if they had been put on the fertilizer, it would have been 100 more carrots than they actually had. Okay. So this is called the average treatment effect on the treated, ATT. What it's going to be is the average treatment effect for the people that were actually on the fertilizer, ATT. Correct. No, you're not averaging across no, Julietta, each person has two potential outcomes. They have one outcome, but two potential outcomes. Okay? They have two potential outcomes. Here. We're gonna do it here. Okay? So here is a situation. Here is a situation where I'm gonna have 10 different or 11 different patients. Okay? If I want to calculate the average treatment effect, I go Y1 minus Y0, that's the individual treatment effect, and I've got individual treatment effects all the way down. If I want to get the average treatment effect, I average over column D. I don't average over the realized outcome. I average over column D. Correct. We cannot observe it. But causal effects are based on potential outcomes, not realized outcomes. That's what Hito was talking about. Hito was talking about the fact that the causal effect is defined in terms of differences in potential outcomes. So when Andy was on the drug, his outcome was a 14. When Andy was on mindfulness, his outcome was a 15. 14 minus 15 is the causal effect of the drug compared to mindfulness. It's a -1. Okay? Betty's on the drug. Her outcome is a 15. Had she been on mindfulness, it would have been a 20. 15 minus 20, -5. Causal effect of the drug compared to mindfulness, -5. So average treatment effects is only based on column D. It's not based on realized. Exactly. Exactly, Zoe. That's exactly what I'm saying. That's what I mean here. What Zoe just said, for those who didn't see it, what Zoe just said is we can't be in two states simultaneously, so we can't both receive and not receive the treatment at the same point in time. So we cannot compare the outcomes of both scenarios for an individual. Correct. And that is called the fundamental problem of causal inference. Since causal effects are defined in terms of those two variables, and you are not able to see them at the same time, you cannot make these calculations. Okay? You cannot make these calculations. All you can make is an associated treatment assignment and a realized outcome based on that treatment assignment. So look, that's going to be a 14. That's going to be a 15. That's going to be a 15. That's going to be a 5. That's going to be a 1, 2, 6, 6, 0, 26. I'm going to know the realized outcomes, but the realized outcomes are not useful for making that calculation. Okay? For making that calculation, because Y is not used to define this, right? Y is not used to define it, but the switching equation is deleting one of the terms. So if you want to know the average treatment on the treated, you just look at the average effect for the people in the treatment group. If you want to know the average effect of the treatment on people not in the treatment group, you have to look at the average effect for the people not in the treatment group. Okay? But you're still, exactly, Yuki's right. So exactly, you get the ATT from the treatment assignment. If I was to change it, that'd become a 14, and the average treated on the treated becomes different. And this other one, for the people not in the treatment, it becomes different. Ah, Jana. No. That is not an estimate. That is not an estimate of the average treatment effect. That is the average treatment effect. You're getting at exactly the point of causal inference. Causal inference does not calculate the average treatment effect. So then what does causal inference do? It estimates it. It gets numbers that are approximately equal to a causal parameter that you have chosen ahead of time that you want to know. And there are at least 3. And Yuki mentioned a 4th. And somebody else said marginal treatment effects. So there's all these different possible treatment effects that you could get. So you have to know ahead of time. You have to know. Yes, sorry. ATT is. Oh, I thought you said treatment assignment, Yuki. I didn't read that right. Exactly. Diff and diff only identifies the ATT. Synthetic control only identifies the ATT. Okay. So when we get back, we're going to do more spreadsheets. Okay. When we get back, we're going to do more spreadsheets. But we've got here this one particular causal parameter. It's a conditional average treatment effect called the ATT. And then there's another one, average treatment effect on the untreated. And it's called the ATU. Seth, we're not getting, Seth, that's what I'm saying. We do not have the ability. We're going to do it together, Anthony. We do not have the ability. Here, I'll delete this. Okay. When we get back, we'll do it together. All right. We do not have the ability for each person to know both potential outcomes. Yes, causal effects are based on potential outcomes, and in the real world, you do not know them. Why? Because remember what we said. They are a priori fixed but unknown. All you know is what happened when the treatment assignment was made. Okay? I don't know the term individualized causal effect. I only know the term individual treatment effect, so I'm not positive what that is, Renz. Yuki asked, can we get AT from anything other than the RCT? Yeah. Yeah, tomorrow we're going to look at ways to get the average treatment effect outside of the randomized control trial. With enough assumptions, you can get any parameter. You just got to know which assumptions are required to get it. Oh, Seth says, if you don't know Y0 when D equal 1, how did we get it? Because this is made up data. This is made up data. This isn't real. This is not real data. The only data you're ever going to have, I messed up. Okay. The only data you will ever have is that column of data. Treatment, realized outcome. Nobody knows those. Just like I was saying, Jeff does not know what his potential wages would have been had he not gotten a PhD in economics. He only knows what his actual wage is in a world where he got one. So the individual treatment effects can never be calculated in this framework. All right? People are wanting steps. They want to see us do it. So here's what we're going to do. Here's what we're going to do. We're going to take a break, 1 hour break. We're going to do this together. I'm going to create a new, sheet right here. I'm going to create a new sheet for us, and then you're going to do it with me. Okay, we're going to do it together. So let's take our 1 hour lunch break. We'll come back, and then we will get in there, and we're going to actually manually calculate this so that you really can see with your own eyes exactly what this is. Okay. All right. Because this is why I go slow. This is why I go slow, because it's very subtle and people don't really start asking the questions until like a little bit of time passes. So let's take an hour break. We'll come back at 1:07 p.m. Go eat some lunch. I'm going to go eat some lunch, and I'll see you guys in a little bit. Okay. All right. See you in a minute. I'm going to do it at the break. I had a big old lunch, and that at my age, every time I have a big lunch, I basically black out and have like a complete fall asleep thing. So I'm gonna try not to do that. So all right, here we had this thing. All right, so here's what we're gonna do. Oh, y'all got it. Good. Okay, so everybody's got this thing, and I don't mind making you editor, but the only problem is it like you'll edit the thing, and so so let me just give you this. Put this in date. Oh, thank you, Julietta. Okay, Julietta put it up there. And yeah, I don't know what's going on with that AI thing either. I didn't understand that. It is for the AI summary, but it was like something left the meeting. I don't know. It's something with the AI thing, and I don't really know. So okay. All right. So first 3 steps again. So here we go. All right. So what we're going to do is I want you to do this with me. We're going to go through these 6 steps. Okay. We're going to go to these 6 steps. And we're going to use the equal sign for all of it. So we're not going to be, we'll do this real quick. Okay. And so we're going to be not doing the like inputting in, except for in one spot. The rest of the time, we're going to use the formulas. Okay. So let me do that now. All right. So fill in number 1, fill in the missing treatment effects. Okay. So go ahead and do that. Okay. So we're going to go individual treatment effects, Y1, Y0. Okay. And what this is a situation with, it's a situation with 11 patients, and each of them struggles with depression. Okay. Each of them struggles with depression, and there's only 2 treatments at this, that they can take. We're simplifying it. There's only 2 treatments they can take. They can either take a drug like an antidepressant, or they can practice meditation, or what's called mindfulness. That's only 2 they can do. Okay. You always have to specify what each of these means. So, some people are like, well, can't Y0 be nothing? Yeah. Y0 can be nothing. Y0 could be anything. It's just got to be a different treatment assignment. All right. So we're going to have we're going to have here that there's 2 treatments, and we're going to see what the potential outcomes are under both. But the thing to remember is that the only reason I know what these are is because this is a spreadsheet that's fake. Okay? Just keep that in mind. The only reason that I am able to the only reason I'm able to do this is because I made the data. Okay. Since I made the data, I know all this stuff. Or rather, sorry, it's a simulation. It's not real. Nobody really knows this. Okay. But if they chose that, then that would be their measure of happiness. And if they chose mindfulness, or rather, if they were assigned to mindfulness, then that's what would happen. So we're going to calculate the treatment effect. Equal y1 minus, minus y0. All right, I can do that down. All right, so look, if he was on the drug, his happiness would be 14. If he was on mindfulness, his happiness would be 15. 14 minus 15, -1. The drug caused his happiness to fall by 1 point when the comparison is mindfulness. Okay. So we did that all the way down. So now we're going to calculate the average treatment effect. Equal average that. Okay. All right. So on average, drugs increase happiness by 2 points, but some people are hurt and some people are helped, but it helped more people in the magnitude, than it hurt people. Okay, that's kind of the net benefits, I guess, were positive. Okay, so assign the units to treatments based on an assignment rule. All right, so we need an assignment rule. Okay, so I'm going to call on somebody, and I want you just to put in the chat, what you want the rule to be. Okay, the rule could be everybody above 6 is going to be put on drugs. It could be every even number put on drugs. It could be whatever you want to do. So Becky, would you mind giving me a rule that you want to follow for putting people in the treatment group? Males on drug. We'll do it like male names. So the American male name, traditional names on drugs. American traditionally female names on mindfulness. All right, great. So Andy, drug. Betty, mindfulness. Chad, Daniel. Edith's a woman. That's my daughter's name. Frank, George, Hank. Ina, female name. We'll say Kelly, traditional female. Mindy. Okay, so the rule was simply males on drugs, female on mindfulness. Okay, and now what we're going to do is we're going to calculate average treatment on the treated, average treatment on the untreated. We're going to go here, equal average, and we're going to select anyone in the treatment group can be put on the drug, and anyone that's got a traditional female sounding name, they're going to be put in the drug category. Okay. All right. Thank you, Becky. All right, let me do another one. So Ivan Guitart, would you give us a new rule? Give us another rule. It could be anything you want to do, any rule whatsoever. Okay, I'm going to skip Ivan. I don't know if you heard me. Jacob, Jacob, would you mind giving us a rule? Oh, well, maybe you said it in the thing. Oh, Ivan. Sorry, Ivan did say it. Okay, I'm sorry, Ivan. I didn't see it on Discord. Okay, Ivan said it. Green names on drugs, orange names on mindfulness. Perfect. All right, so we're going to delete that. Okay, we're going to delete it. So now we're going to go green names 1 1 1 1 0 0 1 1 0 1 0. All right, recalculate. Now look, it was 0.67. So when we did that, okay, when we did that, oop, ATT was 0.67. ATU was 3.60. One more thing. And then ATE was 2.00. Okay. So that's what we're going to see. We're going to see what does that become. All right. So we're going to change it here. Equal average. Those, that. Okay. Then we're going to go average treated on the untreated. We're going to go this. Okay. So now we go ATE didn't change. See that? ATE doesn't change because ATE does not depend on the treatment assignment. Okay. ATT, negative 2.14. It did change. It had been a 0.67. Now it's negative. ATU, big number. Whoop, no. ATU equals 9.25. All right. So the lesson here is that the ATE is independent of the treatment assignment because it is summarizing everyone's treatment effect into a single mean, not just one subpopulation like the treatment group. Okay. But ATT and the ATU are referring to specific subpopulations assigned to treatment or not to treatment. And therefore, under different treatment assignments, ATT and the ATU will differ depending on the amount of differences in the individual treatment effects. Okay, that's all we really want to say right now. That's all we really want to say right now. All we're trying to say right now is just that that's how we calculate it, and that's how we interpret it. Okay, that's how we interpret it. We interpret it as the average causal effect for a group of people on the treatment, average causal effect for a group of people not on the treatment. Okay. All right. So Julietta says, Y1 and Y0 are dependent on the data. Yeah, that's right. I mean, and like you can be like, well, what's that data generating process? It could be like, genetics. It could be some other covariate. It could be like whatever, So yes, that's right. Yes. Got it. Okay. Eduardo's talking. Wouldn't we want ATT? Well, we don't want anything. We don't want anything. The treatment has been assigned, and it has therefore an a priori fixed but unknown value. It's not about what we want. We want it to. Here's what we want. We want to decide up front which of these parameters we want to estimate. And then we want to figure out what assumptions will allow us to estimate it. That's it. That's what we want. Do you want the ATE, the ATT, or the ATU? People have different reasons for wanting which of them. All right, Eduardo says, now what is Y? Y is the realized outcome. And the realized outcomes are based on switching equation. Y equals dy1 plus 1 minus dy 0. That's the equation, and it came from here. This. Each person's Y, realized outcome, is based on, are they in the treatment group or not? And if they're in the treatment group, the realized outcome is Y1. But if they're in the control group, the realized value is Y0. Okay? So we're going to use that equation right there. We're going to use that equation. And I'm going to make it a little smaller. We're going to type that in. Okay? Equal D times Y1 plus 1 minus D Y0. Okay, so look, he's in the treatment group, so I observe 14. See that? That number is that number because he's in the treatment group. He's in the control group, or Edith's in the control group, so therefore D is a 0, so it crosses out Y1. 1 minus 0 is a 1. 1 times Y0 is 1. Y equals a 1. Okay? So this is the realized outcome, and this is the potential outcome. We can even go further than that. We could say in the data set, sorry, not in the data set, not in any data set. Okay, and then you could say in the data set. All right, so this is the only thing in the data set, not counting this. Okay, you know if they are on mindfulness or drugs. Okay, you know that. And if they're on drugs, then you know their realized outcome. Okay, but you never know these 3 columns. You don't know truly Y1 or Y0 because it's kind of a, fixed but unknown value. It only becomes known under the treatment assignment. Okay? So that is the realized outcome. But if we were to do what Becky said, look at what Becky said. Male names: Andy, Betty, Chad, Daniel, Edith, Frank, George, Hank, Ina, Kelly, Mindy. No. Ina, George, Hank. Okay. Notice how when I change the treatment assignment, notice how the realized outcome changes. Now, I don't have this automated, but basically that's what goes on. Okay. Okay. So is this realized outcome? No, the U vector would basically be that right there. It would be this column. That's the U vector right there. That would be that. I'm not going to put that in there because people don't know what that is, but the U vector was referring to the kind of the vector notation for all potential outcomes, potential yields, and potential yield is a treatment effect. This would be like U bar. This would be like U bar. Luvo, let's hold off on that. Well, okay. Let's it's harder to explain it, Luvo, outside until we've kind of moved through the RCT. But let's say that let's say there's a group of cities. Okay, here's one. Here's one. Ventilators. Okay, ventilators. You probably don't want to know the average effect of the ventilator on the whole population. You really would like to know the average effect of the ventilator on people that need to be on ventilators. Okay, so you have to kind of ask yourself, do I care about the entire population or do I care about a group of people on the treatment? Okay, that's what you kind of want to be thinking of. So I typically think of it as like, you know, let's say you've got some job training program, and the job training program is giving, you know, kind of remedial skills. And you know, but it's going to take 2 years. You're going to learn like you're going to learn some basic things like how to handle, you know, frustration with your boss and how to show up on time and all this stuff. Okay. You probably don't want to know the average treatment effect because you could imagine if we were all to get on a job training program that was kind of giving basic job skills, like how to not lose your temper with your boss, how to not lose your temper with the client, all that kind of, you know, how to show up on work on time. And it took 2 years of working in a minimum wage job. You could imagine it actually has a harmful effect on a lot of people who don't need it, but they're like leaving the market to be in it. Versus there's a group of people on job training programs. These people on the job training programs are by nature maybe people that need this. They struggle with anger with their boss. They struggle with anger towards the client. They never come to work on time. And they really need to be in a context where they can get a lot of cognitive and non-cognitive skills that will allow them to be successful. That's the purpose of the program, is to target a group of people that really benefit it. And you really might want to know, you know, is it helping the right people? Okay. No, potential outcome and realized outcome are not going to be the same. Well, sorry. Potential outcome, realized outcome will be one of them. Yes. The realized outcome will be one of these two. Okay. No, the switching equation is always true. The switching equation is always true. It says that if you are on a particular treatment, I then will observe your the potential outcome associated with that treatment. So it's kind of mechanical, Artie. It's kind of a mechanical thing. It's basically saying there's only two potential outcomes associated with a binary treatment. You pick one of the treatments, it then picks one of those potential outcomes because the potential outcome is defined in terms of, you know, a state of the world where you're exposed to that treatment. Does that make sense? So I don't know what you mean by untrue. Well, tell me what you mean by untrue. What's an example that you're thinking of? Be thinking of it, and I'll
Yeah, can I speak here instead of?
yeah, can I hear? Yeah, okay, go for
Yeah,
it.
so my question is basically, like we're assuming that if the drug is assigned, the potential outcome is 14 for Andy and 15 for mindfulness if if mindfulness is assigned. So is it like we're just assuming that this is always going to be the case? If the drug gets assigned, Andy will always have the realized outcome as 14. So like, can it not be like 13.5 or something like that? Or is this
No.
just how the setup is?
No,
for
it'll
this?
never be 13.5 because these potential outcomes are describing an outcome in a world where you are exposed to the treatment, and this is the treatment assignment. This is the exposure. So if these are the outcomes associated with a treatment, and then this is the assignment of the treatment, it's like by definition, this will select it's like an algorithm. It just selects as the realized outcome of the two, you know, like this Y1, it's referring to D equal 1. This Y0, it's referring to D equals 0. So if you're assigned to the treatment, it's like this will materialize because that's what this is.
Okay.
Does that make sense?
Yeah, so I'm not sure if I'm diverting a bit over here, but say suppose like, you know, we have some real world data. So in that case, we'll not have like a setup like this where we know exactly what the potential outcome will be. So
Exactly.
like,
No, okay. We
how do
will
I
never know
reconcile
both of
this
them.
with that?
Huh?
Sorry, my question was just like, you know, I understand what we're doing here, but like I'm not able to sort of reconcile this with what happens if we have like real world data or a real
This
world
is okay. So
RCT.
this right here is real world data. Okay. That's real world data because we do not know. It's as though we don't know any of this. Okay. That's the realized data. That's the real world data. We have a data set with 11 observations. Those people are in the treatment. Those people are in the control. That's their outcomes. But we know under the potential outcomes, we know that this one is referring to Y1 because that's what it is by definition in the potential outcomes.
Okay, I understood now. Yeah, thank you.
Yeah. Ronald says, so mindfulness treatment isn't control, nothing. There really is no such thing as nothing. Nothing is something. So you just have to compare it. You have to make sure that whatever the comparison state is, you just, you know, make sure that that's like defined. If you're going to say nothing, be very specific about what nothing means. If it just means no drug, but everything else is the same, that's fine. But I was saying, you know, it's like a person comes in with cancer to the doctor. Okay. Or these people show up with depression these people show up to the doctor with depression. The doctor's not going to say nothing. The doctor's going to probably do something, but he only has two options. He can either give him drugs or he can give him mindfulness. Okay. That's in this case right now, we're defining the two states of the world as the difference. So all this is to say, you know, you be sure that when you are thinking about D equals 0, it means the same thing for everybody. Okay. So in our case, D equals 0 means mindfulness. But if you just said nothing, or if you said no drug, there's lots of ways you could have no drug. Okay. You could have, they're getting exercise, they're eating diet, they're listening to music, they're like, you know, doing other stuff. You'd have to just be really specific about what is happening in this other state of the world, because it's got to be the same for everybody in order for these average effects to make sense. Okay. All right. So here's what we're going to do. We are going to calculate something called the simple difference in mean outcomes, SDO. All right, we're going to calculate the SDO. And in fact, let's go ahead and just, you know, go ahead and start here. Go to our PO1 and PO2. So let me make sure that we got this. We're going to go ahead and fill this out real quick. Just make sure we're all on the same page now. We're going to do that. All right, so go ahead and let's fill this out again. All right, so I think it's a little bit different, but let's go ahead and fill it out. 14 minus 15. Just fill up all the way down. Assign the treatment. And here's how we're going to assign the treatment. If the treatment effect is 0 or above, non-negative, you're going to put these people in drugs. Okay. So if the drug helps them or does not hurt them, if the drug does not hurt them, put them on the drugs. All right. So if it hurts them, put them on the mindfulness, because the mindfulness it helps them. All right. So we're gonna go here. We're gonna go. That's a negative. So he's gonna go mindfulness, 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 drug, drug. It's non-negative. Remember, it just has to not hurt them. So drug, mindfulness, drug, mindfulness, drug. Okay. So we've got now a treatment assignment mechanism. And I'm calling this treatment assignment mechanism the perfect doctor. Okay. Perfect doctor. Why is it the perfect doctor? Because look at what this doctor has done. This doctor has only put you on the treatment that has the higher potential outcome. So look, mindfulness has a higher potential outcome than drug. So she puts them on mindfulness. For Edith, drug has a higher potential outcome than mindfulness. So she put her on drugs. So the perfect doctor in this scenario, the perfect doctor appears to have the ability to know. Put aside the fact that you don't think it's realistic. I'm just basically saying right now that we're going to have people getting on the treatment. We're going to have people getting on the treatment if the treatment doesn't hurt them. And then we're going to have a group of people get into the control. We're going to have people get in the control if the mindfulness is better for them. Okay. So this perfect doctor is essentially like the perfect doctor is basically someone that just, has like almost telepathy, almost like extra sensory perception. They somehow know this stuff. They're like magicians. Okay. All right. So we assign the treatment to them. I call it perfect doctor assignment. Now we're going to use the switching equation, which is that, to determine the observed, or what I call realized outcomes. So here we go. Equal, remember it's got to go D Y1 plus 1 minus D, which is the control, Y0. Okay, so you can see right here, the person's in the control. In the control, your potential outcome's a 15. So the data that I observe is a 15. This person's in the treatment. Treatment pulls in Y1. Y equals Y1. And all the way down. Okay? No. 0 difference right here. That is a treatment effect. Okay? That's a treatment effect. That means if they were on the drug, their happiness would be on a 6. And if they were on a mindfulness, it would be on a 6. So drugs don't help them. They don't hurt them. Some people are not helped at all by an intervention. Sometimes treatment effects are 0. Okay. And you don't know that because you only are going to observe their realized outcome, but this person has no treatment effect. Exactly. Okay. Okay. So, all right. Calculate the simple difference in mean outcomes. Now let's look real quick at what that is. That is this equation. Okay? That is this equation. Now, since we know that when you are treated, your realized outcome is Y1, we're going to be able just to use, so look, it's like this. Since Y equals Y1, if D equal 1, and Y equals Y0, if D equals 0, we can rewrite this. We can rewrite it. Expectation y d equal 1 minus expectation y d equals 0. This is just a simple difference in average happiness for the drug group and the mindfulness group. That's all that it is. It's just a simple difference in averages of the realized outcome for the two groups. We don't have any confounding. No, Zoe, we're just calculating it. We're just calculating. That's all we're doing. Right now, we're not even interpreting it. We're not talking about it as anything causal. Okay? So we're not doing anything causal. We're just saying, because we're going to take the average. We're going to take the average. This is all kind of like in the population, we're going to take the average of the treatment group's realized outcome. We're going to subtract out the average realized outcome for the control group. Okay? Here, watch. Here's what it's going to be right there. STO. Okay? Equal. Average. The health outcomes for people on drugs, 14, 15, 16, 8, 9, minus average outcome for people on mindfulness, this. I don't think this is right. Hold on. I think I did it wrong. Average. Oh, I did it wrong. This. Maybe. Unless somebody has changed my numbers. It's supposed to be a different number. Huh. Is that what y'all get? 11.5. I get a different, I've done this 1,000 times and yeah, that's it. Okay, well, all right, well, that's what we're going to get. All right, so that's right, negative 4.26. Okay, that's what it is, negative 4.26. Okay, someone came in and messed with it. That's all right, I don't care. So, all right. So, aggregate causal effects. Okay, so we calculate the simple difference in mean outcomes. No, I usually, the numbers are usually, the numbers, I must have changed them without knowing it. No, this is right. I just, I must have changed them. It's fine. So I just, you know what, it doesn't matter. So, okay. So that's the, on average, let's interpret it. So STO. Drug group happiness is 4.3, 4.267 points lower than mindfulness group. Does that mean drugs cause, on average, happiness to fall 4.267 compared to mindfulness? Yeah. Okay. All right. So yeah, I'm like so distracted because I know that it used to be a negative 1.9. So I must have changed it. I think I changed it for class last week and whatever. So all right. All right. Number 5. So drug, so we want to know, is this 4.267? Is this 4.267 like, corresponding to corresponding to anything? Right? So let's look. Calculate the average causal effects. So let's calculate this one. Average. It's a 2. Okay. And then we'll do the average treated on the treated. And then we'll do the average treated on the untreated. Okay. All right. Okay. So that's the SDO. It's a negative 4.63. And notice that's definitely not the average treatment effect. It's not even the right sign. And it's not the average treated on the treated. And it's not the average treated on the untreated. Okay. So this is like, not correct. This is not a causal parameter. It's not a causal parameter. Right. So let's take a 15-minute break. We'll come right back. And then what we're going to do is we are going to decompose this negative 4.267 into these 3 sums. Okay. We're going to decompose it into the sum of 3 things. Okay. So we're going to come back in just a minute and we'll do it. All right. So to come back at 3 minutes on the hour. All right. So somebody says, Scott, I know why you got oh, didn't I? You are assigned treatment on whether treatment effect is non-negative, which is 0. That's fine. Okay, it's gonna be fine. All right. So, all right. So here's what we got to do. All right. Here's the big. I'm gonna give you a peek at what's coming. All that stuff. Okay. That's what we're about to do together. All right. So, this is where we're going to end up. This number here, negative 4.27, that's this number, negative 4.27. And negative 4.27 is equal to the average treatment effect, this, plus average Y0 for the treatment group, which is going to be that. All right, so it's going to be average Y0 for the treatment group minus average Y0 for the control plus 1 minus pi ATT minus ATU. I know what you're thinking. I don't know what any of that stuff means, and I don't understand where you got it from. That's why we're going to do it together. Okay? So before we get started, we are going to look closely at the definition of the average treatment effect. Okay? We're going to look closely at the definition of the average treatment effect, and I'm going to do it over here. All right? I'm going to do it over here, and I'm going to put this formula here, because that'll be a little easier. Whoops. I'll put it right there. All right? So I've got this formula, got 2 formulas. that are expressions of the average treatment effects. And just so this isn't distracting, I'm just going to get rid of that. Okay, so here we have two formulas, two ways to express the ATE parameter in terms of, well, I'll just do it like that. Okay, two ways to express the average treatment effect parameter. You can either think of the average treatment effect as a weighted average of those two terms, or you can think of it as the sum of all those conditional expectations. And I want to show you that, in fact, it is the same thing. Okay, so this is going to be formula one. We're going to put it right there. And so what we're going to do is we're going to say, that's the average treatment effect, average Y1 minus average Y0. We already know it's a 2. Average Y1 minus average Y0. Average treatment effect turns out to be a weighted average of those two other parameters, just that the weight is the number of the share of the population in the treatment group plus the share of the population in the control group. Okay, so watch. First, we got to get the share of the units in the treatment group. Equal average this. All right, so 45%. So the weight on the ATT pi is 0.4545. Okay, so the weight on the ATU, 1 minus pi, is, 1 minus 0.4545. 0.5455, 0.5455. Okay? All right. So what we're going to say is we're going to show that AT equals 0.4545 times negative 2.14 plus 0.5455 times 9.25. Okay? So let's do it right here. Equal this times that plus 1 minus this times that. Should be equal to a 2. Okay, it was not. I did something wrong. What am I doing wrong? Oh, is it? Oh, I didn't do it right. My bad. Equal average. I forgot. We changed it. That's the ATT. That's the ATU. There we go. Okay, I was about to panic. So look. Yes, thank you. Thank you, Shreyoshi. So see how it is? Average treatment effect can be calculated two ways. One, take the average of the treatment effect column. That's what that is. Two, take a weighted average of the two conditional average treatment effects. That's what this is. Or three. The third is I can distribute these terms right here, open up this average treated on the treated. So watch this. Pi times expectation Y1 for the treatment group minus pi expectation Y0 for the control group. That right there, I got to write this down for you. That right there, remember, ATT expectation Y1 equal 1 minus expectation Y0 D1. So there's our two definitions. And so if I was to just do like, pi, then it would become, pi. And if I was to do, 1 1 minus pi it'd be this. Okay? And that's what this is. So here we have, I took pi ATT, and I rewrote it as pi expectation y1 for the treatment group minus pi expectation y0 for the treatment group. And then down here, I did 1 minus pi y1 for the control minus 1 minus pi y0 for the control. So notice what I've done. I started with the definition of the average treatment effect. I showed that that's a weighted average of those two conditional parameters. Oh, thank you. Thanks, Khaing. Khaing pointed that out. Yep. Okay. So that we showed is, is true. We did that one, and that one was right here. Okay. That one, we did that right there, weighted average. And now what we're going to do is we're going to take this, written form to the ATT. We're going to move some things around. And I'm going to show you what we're going to do to move around. So we're going to group together the ATT ones. Okay, there's those. And then we're going to do these right here. And I guess I could have, I don't know why I didn't do that. So we'll just go that. We'll go like that. And we'll go like that. And then we'll go like that. All right. Okay. So I'm going to take the pink ones. I'm going to show where they went. So there's expectation y1 for the treatment group. There it is. Okay. There's expectation y0 for the treatment group. That's not it. There it is. Okay. So there's that one. Let's do the green ones. 1 minus pi, expectation y1 for the control. There it is, 1 minus pi. And in fact, it's actually plus sign. Put that plus sign there. Okay, there it is. And then minus, you gotta put that minus sign in. Okay, so then we're gonna go minus 1 minus pi. There's the minus. There was that thing right there. That's what that is. Minus, take the minus out. Take the minus out, and then you got plus that. Okay, do you see what I did? So what I did was I took, again, the main definition, the weighted average definition, distribute the terms, rearrange. Okay, so you can write down this last one is called the law of iterated expectations. Okay, you can express a conditional, you can express a mean as a weighted average of conditional expectations, but put that aside for now. We're going to call it LIE method, law of iterated expectations, but for us, it's just a matter of steps. So the average treatment effect is equal to pi y1 for the treatment plus 1 minus pi y1 for the control minus pi y0 for the treatment plus 1 minus pi y0 for the control. All right, let's do that one. I wrote it down right here. Okay, so we just go all the way down. Pi. Average. We got to go y1 for the treatment. Okay, plus y1 for the control. Plus pi y0 for the control plus pi y0 for the control. So it's y0 for the treatment Okay, of course, I did something wrong. Average, 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 average. Unknown range name average. Ah, there it is. Nope. That's not it. All right, so it did B21 times. Ah, thank you. Thank you. Yep. It should be plus minus. Yep, thank you. So we go, should be, thank you so much, minus, minus, right? Is that what it is? Let's see. So it should go plus, plus, minus, minus. Yep. All right, so let's do it again. So plus, 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 minus, minus. There it is. Same thing, right? Same exact way. The definition of the average treatment effect, the definition of the average treatment effect is equivalent to a weighted average of the two causal parameters or the sum of those four terms. So we're going to use the sum of these four terms. This is what we're going to do. So we're not going to look at that. So we're going to look at the average treatment effect definition. So this is the definition of the average treatment effect. We're going to look at the definition of the average treatment effect as the sum of those four conditional expectations. So all this is right now is the definition. It's just the definition. It's not a theorem. It's not a hypothesis. It's not an estimate. It's just a rewriting of a mean. Okay, it's just a rewriting of a mean in terms of these weighted underlying elements. And we showed that it's essentially whatever, that's simpler, but it's actually equivalent. It's equivalent to that. We do the decomposition so that we understand the source of bias in any estimate. That's the purpose of this. The purpose of this is to understand why is negative 4.27, why is the SDO not equal to 2? Why is the SDO equal to negative 4.27? We want to understand the biases inside this, okay? All right, so we're going to make it a little simpler, all right? So this right here, that's going to be the letter A, that's going to be the letter B, or that's going to be the letter B, letter C, letter D, letter E. Okay? Rewrite it. Average treatment effect, pi expectation Y1 for the treatment group plus 1 minus pi expectation Y1 for the control minus pi expectation Y0 for the treatment group plus 1 minus pi expectation Y0 for the control group. All right. I don't skip any steps because this is crucial. It's one of the most important things it's the foundation for the whole class. We have got to understand what some things mean. So here's the average treatment effect. First step, get rid of these parentheses, all of them. Pi A, pi A. B, 1 minus pi equals B minus pi B. B minus pi B. Minus pi C, D minus pi D times negative is minus D plus pi D. Okay? So this is still, right here, still the definition of the ATE. Okay? Still the definition of the ATE. Now what I'm going to do is I'm going to add a 0. I'm going to add a 0 to the right-hand side. All right? So look at this. 5 equals 2 plus 3. Right? Always. What about 5 equals 2 plus 3 plus 0 plus 0? Nothing changed, right? So one of the features here that we're going to do is we are going to add zeros to the right-hand side. And if you add a 0 to the right-hand side, the identity doesn't change. The equality still holds. So the equality there was equal to the sum of that, and this is still equal to the sum of all that. But when we added in these letters, we introduced terms that we're going to use. Okay. So first step is to move this stuff around. So we're going to move, first thing we're going to do is we're going to move everything. Sorry. We're going to move everything over here. Okay. So look, E minus pi A minus B plus pi B. Notice what I've got here. It's flipped it around. All the signs are flipping because I moved all of this to the left-hand side and then switched it over so the equal signs would stay the same. Okay. So now we know that if I move all this over here, then, the sum of all this is equal to 0. They're all going to cancel out. Okay. No, the bold is the stuff I added. That's all that it is. I actually, you know what? That's a good question. Why did I do that? Well, I originally did it here, illustrate something, but you're right. I need to get rid of it. Ignore the bold. This bold I want you to see. This bold I want you to see. These others aren't really matter. Sorry about that. I'll fix that. It's a good comment. Okay. Watch what I'm going to do now. Negative A. Going to move it to the left. Positive D. Going to move it to the left. Okay. So now look what you have. A minus D equals the average treatment effect. But it's the average treatment effect plus bias. What is A minus D? A, average Y1 for the treatment group. D, average Y0 for the control group. Where have we seen that? It's the SDO. It's the 4.267. Average Y for the treatment group minus average Y for the control group is the same thing as average Y1 for the treatment group minus average Y0 for the control group. Okay, so we go over here. This is the SDO right here. This is the SDO. This is the average treatment effect. This is some bias stuff. So the SDO is equal to the average treatment effect, but it's biased unless all of that is equal to 0. If all that was equal to 0, then the simple difference in outcome would be the average treatment effect. All right, so let's group some terms. C minus D. There it is. Okay, so I moved it over here. This is the STO plus average treatment effect plus a special term. All right, and then all I'm going to do now is just simplify that expression. I'm going to simplify that expression by pulling out the common terms. A minus pi A is equal to 1 minus pi A. Negative B plus pi B minus 1 minus pi B. D minus pi D, 1 minus pi times D. Negative C plus pi C is equal to negative 1 minus pi times C. You see that? All I did was pull out the 1 minus pi terms, move something around. Last step. I am going to take my 1 minus pi A and my 1 minus pi C, and I'm going to put them together. And then I'm going to take my, minus sign, 1 minus pi B minus 1 minus pi D. So I'm grouping these together, and I'm getting this. Okay? Now, what is this? Right here. Let's look at A. A minus C. Here's A. Average Y1 for the treatment group is A. Average Y0 for the treatment group is C. A minus C equals expectation Y1 D equal 1 minus expectation Y0 D equals 0, D equal 1. What is that called? Where have we seen that? Anybody recognize this? ATT. Thank you, Ivan. This is average treatment effect. Expectation Y1 minus Y0 is average treatment effect notation for the treatment group, equal 1, or ATT. B minus D. B. Average Y1 for the control group minus average Y0 for the control group. B, D. Control, control. 0. ATU. All of this is still just based on the definition. That's all we've done. It's just substituting terms in. Okay? So now we have this right here. Simple difference in outcomes is equal to the average treatment effect plus the C minus D term plus 1 minus pi ATT minus 1 minus pi ATU. So now I'm going to replace the letters with their correct terms. All right? Simple difference in outcomes. Like the average happiness for the drug group minus average happiness for the mindfulness group. That's all it is. Look at the average mortality for people on ventilators. Look at average mortality for people not on ventilators. Is that causal? We're going to do it together right now, Anthony. We're going to do it together on a spreadsheet. Okay? We're going to do it together on a spreadsheet. We got the average treatment effect, which came out of that decomposition, plus this term, plus the sum of those, and we rewrite it. Anytime, so here's what we're saying. Anytime, whether it's in an RCT or not, that you compare average outcomes for two groups, one treated, one not treated. It will always be equal to the sum of those three rows on the right. ATE, first row. Selection bias, second row. Heterogeneous treatment effect bias, third row. Anthony, I'm sure, is not the only one who's lost, so I have an exercise. Okay? I have an exercise. So here's what we're going to do. Here's what we're going to do. We're going to go through the perfect doctor exercise twice. Twice. Okay? We're going to illustrate this decomposition together. What you are going to do is you are going to calculate the STO, the average treatment effect, this term, and this term. Okay? So let's do it together. Here we go. Now we've already done average treatment effect, average treated on the treated, average treated on the untreated. And so we know right now this one yeah, I'll change it. Yeah, I will. Sure thing. Okay, let's look at this. All right, let's look at this. So all I want you guys to do, all I want you to do is calculate that, calculate that, calculate that, calculate that. We're going to do it twice. Each time we're going to try to understand it. Okay. All right. So I'm going to delete it. Do it again. Okay. So step one, calculate the SDO. Equal average minus average what? It's like, why did it just change? It had been that -4 number. E9. E13 is messing it up. But it's supposed to be that. Did I do something wrong? Let me try it again. Equal average. This, 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 minus average 0, 0, 0, 0, 0, 0. Better be that 4 number again. Good. Okay. I was doing something wrong. So that's when you do math at the board, you can't ever get the answer right. That's the thing you learn as a teacher. If it's like addition and you try to do math on the chalkboard, you will always get it wrong. That's what I've learned in my 20 years of being a teacher. So -4.3. All right. So we've done this. Okay. We've done this. All right, Anthony. So Anthony should be able to calculate this. You got that, Anthony? I just want to stop. Does everybody have this? We'll see in a second, Mauricio. Has everybody got -4.3? Is anybody having trouble getting it? About to sneeze. Calculate the average treatment effect right here. Equal. No, you're good. You're good, Mauricio. I was just saying, we're about to get to it. It's easier. It's actually easier to explain it if you do the calculations first. It's easier to explain it if you do the calculations first. So there we did the average treatment effect. So we got SDO, -4 something. That's a 2. Now we got to do this. This is selection bias. Okay. This is selection bias. So we're going to calculate expectation Y0 for the treatment group. Yes. LTM, law of teaching math at the board. All right. So we got on average. So here it is. Okay. Actually, let's just do the calculation first. Okay. Then we're going to go back and interpret this stuff. All right. So that's a 3. Notice what it is. It's the average of the treatment group Y0. This, that. 5 numbers. 1, 2, 3, 4, 5. 5 numbers. Okay. Now we're going to do it for the control group. Equal average for the control group. So we're going to go, it's only Y0. This, that. They're very different, right? Back up for a second. Here's all I want you to say. The treatment group and the control group on average have different values of Y0. That's all you got to say. Treatment group and control group have different values of Y0. Treatment group, its average Y0 is a 3. Control group, its average Y0 is a 14.7. All right. So this one is smaller than that one. So that one right there is a 3. That's a 3. And that's a 14.7. So we're going to put the sum of the two right here. Equal 3 minus 14.7, negative 11.67. So here, selection bias just means that the mean of y0 for d equal 1 is not the same as the mean of y0 for d equals 0. They're different from each other. The two groups are different from each other, not with respect to race or sex or age. They're different with each other with respect to the potential outcome. And it can feel a little odd because you've just learned potential outcome this morning, so it can be a little odd, you know, but that's right now all you're going to say, okay? We need to get the ATT now. Equal average treatment effects. And the average treated on the untreated. Okay. And then we got to get pi. Okay, we got to get pi. All right, so look what we got. -4 something. -4 something. 2. Selection bias. -11.7. 1 minus pi is going to be 1 minus that number. It's going to be 0.55. Yep. Hold on, Jessica, 1 sec. And then ATT minus ATU. Okay. Okay. We haven't really, the reasoning for selection bias, Jessica, the reasoning for selection bias is simply that the two groups of people, treatment group and control group, on average, do not have the same values of y0. It's all that it means. Now, it's deeper than that, but mechanically, that's all it means. Selection bias is simply the difference in two means. Just the difference in two averages. It's just that it's a particular average that we're talking about. It's the average of y0. Okay? All right. What we're going to do is, we know this is equal to -4 point whatever. And if this is an identity, then this -4 whatever, that should also be -4 whatever. So let's add these together. Add the average treatment effect to the selection bias, share of units in the control, ATT minus ATU. Okay, we're going to put it right there. Equal 2 plus selection bias plus 1 minus pi, parentheses, star, ATT minus ATU. And if I didn't make a mistake, which there's 50-50 chance I made a mistake, but if I didn't make a mistake, it should be -4.267. -4.267. All right? Okay. I want everyone to open PO2. Oh, man. Somebody changed it. You know what? Doesn't matter. I want you to go to PO2. It's clean, okay? It's totally clean. I want you to redo it yourself, okay? Redo it yourself. Let's take our break. I know you're almost lost. Zoe, you got to work it out yourself. You got to work it out yourself. Let's go and spend our next break. Let me just double check that that's right. You're going to actually do the whole thing over again. Okay? You're going to do the whole thing over again, and you're going to fill out this perfect doctor, realized outcomes, fill this out, do the decomposition. It's right here. Okay? We're going to come back in 18 minutes. All right? You got 18 minutes to fill this out yourself. I'm not going to put any music on. Put it out. All right? and we'll come back in 18 minutes. All right. And write down your questions, put them in chat and Discord, and we're going to try to answer them as a group. All right. All right. So we'll come right back.
I think you're muted, Scott.
Thank you. Okay, we're going to do this together. And as you have any questions, you just text them or whatever. Okay, so let's do it again. Equal. Equal that. All right. Scroll down. Perfect doctor. 0, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1. Realized outcome equal D times Y1 plus 1 minus D times Y0. You always want to use the switching equation. Whoops, just happened. You always want to use the switching equation because we're going to use the switching equation a lot in the class. And the more that you use it, the more you understand it. Okay. All right. So we got the realized outcomes. We got the treatment assignment. Let's get the average treatment effect. Should be a 2. Average treated on the treated. 7.4. Average treated on the untreated. Negative 2.5. Okay. Now we do our selection bias terms. Y0 for the treatment group. Here, here, here. Here, here. Y0 for the comparison group. Here, 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 here. Okay. Selection bias is the difference between the Y0s and the two groups. And then we get our average number of people in the treatment group. Okay. SCO equal average negative 4.27. And then, so that's that, negative 4.27 calculated manually, then calculated as the sum of the terms. Equal average treatment effect, selection bias, weighted difference in the returns to the treatment for the two groups. Oops. That's it. It's called the heterogeneous treatment effect bias because the drug group benefits differently from the treatment than the control group. They have a different return. And if the goal is to estimate the average treatment effect with the SDO, it is a source of an additional bias. Okay? All right. So here's what we need to do. Here's what we need to do. We need to understand this stuff better. We need to understand this stuff better. Okay? Let's try to figure out what this means. Let's try to figure out what this means. We know it's called selection bias. Okay? We know it's called selection bias. But why is it called selection? That's what we want to know. You can tell it's a bias term because if that's our goal, then if this is not 0, it will always be biased. So this is bias. But what does the word selection mean? All right. So to understand selection, let's figure out what these averages are. All right. Okay. Treatment group. All right. So what are we looking at? Y0. Y1 is happiness if on drug. Y0 is happiness if on mindfulness. All right. Okay. So expectation Y0 is average happiness on mindfulness. Okay. So then the question is, what does expectation Y0 d equal 1 mean? What does expectation Y0 d equals 0 mean? Which of these why aren't they the same? Okay. All right. So I'm gonna call on names. I know nobody likes getting called on, but we're gonna do it anyway. Miguel. What does what's that mean? All right. So while you're thinking about it, it's a 3. It's equal to 3. Okay. All right. So what's it mean though? It is counterfactual. How'd you know that, Eduardo? How'd you know that? How can you tell that this is counterfactual? Exactly. Ivan's right. It's based on a potential outcome, and it's the potential outcome that we do not observe. Miguel and Ivan nailed it. Eduardo, Miguel, and Ivan nailed it. We do not observe this. And let's write down what it is. Expectation Y0 d equal 1 is average happiness on on mindfulness for those on drugs. That's it. You got to say it out loud. Just say it to yourself because it's very awkward. It's very awkward to say. But look, the D equal 1 part right here is talking about a group of people. But Y0 is talking about a state of the world. They're not the same. This is a group of people. This is an exposure to a treatment in a state of the world, regardless of whether it happened. Yes, for those assigned to the drug. For those assigned to the drug, what would their happiness have been had they been on mindfulness? It would have been a 3. Expectation Y0 d equals 0. $14.7. Okay, so let's figure out what that one is. Expectation Y0 d equal 0. All right, so Alessa, you want to take a stab at this? What is Alessa, if you're listening? What in the world is that? What does that mean? Imagine you were explaining it to
Scott. In England,
Alexa.
the name Alexa means
Alexa. Stop. Stop.
In Greece,
Alexa.
the name
Hold on,
Alexa
sorry.
means protector of mankind.
Oh gosh. Quit.
Just so you know.
Alexa was telling me the answer. All right. So Alessa. That's what it said. Okay, Alessa, what does this mean? Imagine you were explaining this to, oh my gosh, all the Alexas are talking. I'm gonna have to whisper. What does this mean? Average Y0 for the control group. Alessa, I bet you get that all the time. I bet all the time people say your name and it makes their Alexa app talk. I just realized that. Yes, exactly. All right. Oh my gosh, it's all my Alexas are talking. Is average happiness on mindfulness for those on mindfulness? And it is observed, okay? But the point we want to make is that it's a state of the world for two different groups. Same state of the world, two different groups, and we observe it. It's the only one that we observe, actually. We observe this part, and then we observe this one, but the rest of the stuff, can't observe that, can't observe that. Okay? But the main thing you want to focus on, is that these two groups are different from one another. Now, I want to say something. Anna said, maybe people who take drugs are naturally unhappy, right? And that's kind of the point. Anna kind of nailed it. In a world where every one of these people, okay, in a world where every one of these people had been exposed to the same treatment, notice the ones who were not on the treatment were much worse off. They were much worse off. Their averages, they were unhappy outside of the drug. They were unhappy on the mindfulness. Okay? So they're not really, so this is kind of the thing. These two groups are not really comparable to one another on Y0. They're very different with respect to Y0. And that is selection bias. That is selection bias. So if you think back to the ventilators and COVID. Okay. Let's say D equal 1 is vents, D equals 0 is no vents. And Y1 is mortality on vents, Y0 is mortality not on vents. Okay. Expectation, Y0, D equal vents. Expectation, Y0, D equal no vents. Okay. Which group is going to have a higher mortality rate in a world where they aren't on ventilators? Do you think that the group on vents dies at a higher rate than the group not on vents if neither were on vents? Is it the same? What do you think? What do you think? You've got this group of people going on a treatment, right? Exactly. That's exactly right. That's exactly right. We can't know it, but we can kind of deduce it, Anna. We can kind of deduce it, and Becky's kind of got it right. The reason that they're put on the ventilators, think about it. The reason that they're put on the ventilators is because they're in such danger if they weren't on the ventilators. Y0 is not on the ventilators for a group of people that get on it. Exactly. Exactly. And that is the source of the bias. That is the source of the bias. Exactly. And that's right. Neil's nailing it. Docs put them on the vents. That is not random. It's because of their condition. In a world where they weren't on the vents, Y0, they would be high risk. You got to figure out a way to get your brain to feel comfortable talking in terms of the potential outcomes. There's a lot of this that feels very natural, but you got to stick it. You got to get used to talking in terms of the potential outcomes, because the rest of the class is all in terms of the potential outcomes. The whole class is about trying to find situations where we can delete that. That's what we're trying to do. But the modeling tradition, Heckman, Wolpen, others, The modeling tradition of causal inference will usually model that. They'll model it and delete it. But what we're going to do is the experimental, the design tradition. And what makes the design tradition different is that the design tradition does not delete it with a model. It doesn't guess at what that is and then try to substitute it in. It uses situations where it's plausible that those are the same. That's the natural experiment kind of approach that was taken. Probably, Divya, in the real world, people do not randomly end up on vents. In the real world, all right, here's what I'm saying. In the real world, people do not randomly decide to get on ventilators. They select into ventilators based on potential outcomes. And if they select into vents because of Y0, then it will create unequal second row, i.e. non-zero selection bias. That's what does it. Selection means that the assignment to the treatment is actually directly connected to Y0. Okay? Exactly, Seth, exactly. We're thinking to ourselves, what we're thinking about is that we know how doctors work. Doctors put people on vents because if they don't put them on the vents, they will die. And they didn't put you and me on the vents because we were okay not being on vents. Two different groups, two different treatments directly related to their vulnerability had they not been on the treatment. And that's what selection bias means. I'm going to do it right now. Exactly, Nina. And over here in the chat, there's an interesting conversation about ethics, right? And I'm just going to kind of read it out loud. Divya says, so we can't have randomized experiment in the vent case. Neil says, you could, but it would be rather unethical. Becky says, if you wanted to establish whether vents worked, you could randomize people who were eligible for vents to have them or not. But it's not ethical if you already know vents work. People are now talking about the rules governing experiments in medical trials. You're not allowed to harm people. But if you don't know what it is, we're going to see why we do these randomized experiments. So, okay. So eliminating the selection bias requires understanding the selection mechanism. That's the key. You got to know why the people are in the treatment. You have to know ahead of time. All right. So let's look at this independence and selection bias. So there's a really great paper. I've got it in the readings. I encourage you to read it. It's by Peter Hull, Michael Causal, Chris Walters. Peter Hull and Chris Walters were Josh Angress students at MIT. Angress won the Nobel Prize. And Colasar was a Hito Embens student at Harvard. Embens won the Nobel Prize. So when their advisors won the Nobel Prize, they wrote this really nice economic history of causal inference that goes back to the beginning. And the history of causal inference in economics has kind of like two twin, starting points. One of them is Princeton University's industrial relations section in the 1970s and 1980s. In the 1970s and the 1980s, labor economics, empirical labor economics, okay? People working with data, studying inequality. It was usually some kind of inequality type of question, or even returns to education is a inequality kinds of question. So there was all this empirical work, and it slowly became clear, particularly to these people, the labor economists in the industrial relations section, or what's called the section, it became clear to them that all of the empirical work that was being done in labor was garbage. It was complete garbage. There's all kinds of testimony to it at all. You had people that were basically just absolutely did not, let's see. I'll put it in there. Looks like it's not in there, but I'll get it and I'll put it in there in just a minute. I thought I had it. Oh, you know what? I can do it. Hold on. All right, there you go. So now it's there. So all the empirical work was broadly thought to be not very good. David Card has written about that in a speech in 2012. If you watch my David Card interview, he talks at length about it. Josh Angrist talks about it. Orley Ashenfelter talks about it. I have all these interviews with these guys. So Orley was the head of the industrial relations section in the 70s and 80s, and maybe even in the 90s. He became the editor of the flagship journal for economics called the American Economic Review. He was editor for about 20 years. Hugely influential man. He probably almost won the Nobel Prize with Card, which is a tangent. But anyway, Orley was David Card's advisor. He won the Nobel Prize in 2021. He was Bob Lalonde's advisor, and David Card and Orley were both Bob Lalonde's advisor. Josh Angrist was the student of David Card and Orley Ashenfelter and a bunch of others. Janet Curry, John DiNardo, who's no longer with us, Steve Pischke. Alan Kruger was a faculty member at Princeton working in the industrial relations section. And this group of people are responsible for this, what's called oftentimes the credibility revolution or causal inference as you know it. That's the group. It starts at Princeton and then it goes to Harvard. I'm going to kind of talk about this a few times. So Miguel asked me to repeat something. So Miguel, historically, there were two ways, broadly, okay, you can summarize like this. There's two ways that selection bias here gets deleted. One is the way that Princeton, with the Princeton Industrial Relations section, all of those guys and women and their students and their collaborators end up doing it. Instrumental variables, diff and diff, matching, synthetic control, all this regression, discontinuity design. It's a particular kind of approach that typically uses these natural experiments or randomized experiments or quasi-random kind of assignments. And we're going to see why those are so special. But the other is people like Jim Heckman, John Rust, Jim Heckman, Ken Wolpen, Petra Todd, Chris Tabor. There's like a bunch of other people that would approach the same questions in labor and not really lean as much on, I mean, not always, it's a bit of a strong statement, but they might try to build in some assumptions that would allow them to what they felt like was eliminate this, but it would require some theory, okay? And it would sort of eliminate it. And in the 90s, like that was kind of the competition. The competition typically was between these like what we call design-based methods, which is everything we're doing in this class. It's all based on the ideas of the experimental design, and the model-based methods. Model the selection bias and remove it mechanically. They've both been extremely influential. They're both very important, okay? Both constitute different approaches. These days, they're a little bit more complementary, but our workshop focuses on the first one, all right? because that's the one that's oftentimes, as we were saying earlier. No, it's called labor by design, Ronald. Sorry. I named it labor by design. Oh. Okay. All right. So, all right. So selection bias, what is it? Selection bias is when one or both potential outcome, mean potential outcomes differ by treatment status. And that means something is going on with these two groups that's pushing them in the treatment for reasons that are directly related to the pieces of the treatment effects themselves. Okay? So the source of the bias in causal inference is when people sort into the treatment or select into the treatment because the treatment assignment mechanism is based on Y0, Y1, or both. All right? And design is the experimental design rooted in Fisher and Neiman's work. The section took the experimental design as a guiding principle and began to develop more and more natural experiment methodologies where the variation in the treatment followed what looked like a random assignment. We're going to see why that was so special. Oh my gosh, really? All right, well, I want you to be able to get it. Okay, it'll go now. All right, so what you've got to be thinking about is this thing we've been talking about, which is the mechanism by which the treatment is assigned. The mechanism by which the treatment is assigned. And we said there was a thing called the perfect doctor, and the perfect doctor is basically an assignment mechanism where each person goes into the treatment only if it helps them. Heckman has constantly, James Heckman, who won the Nobel Prize in 2000, I think, has regularly called this the Roy model. When the selection into the treatment is based on the returns to the treatment, it creates selection bias and heterogeneous treatment effect bias, right? And here's the deal. To the economist, step back for a minute. To the economist, and frankly, probably all of the decision sciences, psychology, sociology, all the social sciences, to some degree or another, they think a Roy model is probably true. Why? What is a Roy model? Roy model means that I did something because I thought it would help me, and I avoided something because I didn't think it would help me. What does it mean to help me? Treatment effect. I go to college because when I go to college, this is my wage. Had I not gone to college, this would have been my wage. I only go to college if I think that's positive. Now, that doesn't describe everybody. And the younger you get in life, the less likely it is. But it's probably getting at a particular kind of selection mechanism that we need to be thinking about versus randomization. Randomization would be an assignment mechanism, okay? But rarely is it something that you and I are doing. Have you, Pedro, re-downloaded? I uploaded today. Yeah, I update. You'll need to re-pull. Okay. All right. So there are 3 ways that we can face selection bias. You can have people select on Y0. You can have people select on Y1. You can have people select on the treatment effects, or what's called selection on gains. And here's what it means. Selection on Y0 means that the treatment group went into the treatment or the control group didn't go into the treatment. They kind of have the same meaning, all right? One group goes into the treatment, one group doesn't because of what would happen if they didn't do it. That would be the ventilator. Kind of see, well, that's at least the ventilator. Okay, that's at least the ventilator. Selection on Y0. I'm going to do this because if I don't do it, something bad or not is going to happen to me. Okay. And if you got two groups of people that are looking at their particular Y0s and they're saying, if my Y0 falls below a certain number, I'm going to go into the treatment. Otherwise, I won't. Then you'll have two people sort of separating, but they're going to be separating based on Y0 versus Y1. Y1 says, I chose the treatment because of what's going to happen to me if I get on the treatment. Okay, so maybe they're looking at Y1, they've got their Y1, and they're thinking to themselves, well, if Y1, my potential outcome in a world where I'm treated goes above a 10, I'm going to go on the treatment. Well, that means anybody whose Y1 is less than 10 isn't on the treatment. Anybody whose Y1 is above a 10 is on the treatment. If you think about that carefully, that means that the average Y1 is going to be different for the two groups. Okay. And then there is the treatment effect. And our situation, this was the Roy model. Ours was a Roy model. Perfect Doctor says, go into the treatment if and only if the treatment helps you. Y1, Y0. It's not just Y1 and it's not just Y0, it's both. Yeah, let's see. Yeah, let's do college. Let's go. College is the treatment and wages are the outcome, right? And let's do happiness. I like doing happiness. Happiness is the outcome, right? So Y1 is happiness if you go to college, regardless if you did. Y0 is happiness if you don't, regardless if you did. Okay? If you are choosing to go to college, if and only if Y0 exceeds some number, what that would mean is, no, it's not, unfortunately, because they're not actually annotated. It's all Zoom. I've tried to annotate it. It's a complete nightmare. So I don't do it. If you're choosing to go to college because you care, you think if you are choosing to college because you think you'll be unhappy if you don't go to college, that's selection on Y0. Okay. Hey, Sergio, it's actually Foundations. I merged it. You gotta download the newest version. You gotta download the newest version. You gotta pull. You gotta pull the newest one. I updated it today. It's the Foundations one. Okay. So that means if you're choosing to go to college because you think you'll be unhappy if you don't go to college, that's called selection on Y0. If you go to college because you think you'll be happy because it's more like this, because of your happiness level at college, that's selection on Y1. And if you go to college, if and only if college causes your happiness to go up, that's selection on Y1 minus Y0, or selection on the gains from college. They're all technically a little different. It's different kinds of treatment assignment mechanisms. Some treatment assignment mechanisms may be based on one variable. Could be either one of them. Some could be based on this one. And usually the right way to think about it, just think of it like this. The easiest thing to do is just imagine a case where there is some threshold where if that variable is higher than that threshold, the person goes on the treatment. So let's say that, you know, if y1 greater than 10 d equal 1. Okay, so anyone whose y1 is less than or equal to 10 doesn't go to college. Anyone whose y1 is more than 10 goes to college. Happy people, people whose happiness at college is high, go to college. Okay. So that's kind of like these are the things to practice. This is kind of the language to practice. No, Allie, the issue with this potential outcomes approach, I mean, you can reason some of this out, but, you know, off your intuition, like we were doing with ventilators, but technically, there is no theoretical restrictions being placed on the potential outcomes framework. I mean, it is extreme. You know, it's invented by statisticians. It wasn't invented by behavioral scientists, economists, demographers, sociologists, psychologists. That's not really the source of it. So there's nothing about like rational choice or, you know, some sort of intentional behavior. None of it's in there. Yep, these are the only ones. These are the only ones where are these, because the source of the bias is always going to be the potential outcomes. It would be like this. It would be like this. It would be basically like, so let's say this. Let's say selection on Y1. Okay. Treatment if and only if Y1 greater than 10. Okay. All right. So you look over here. Okay. Now notice he's not supposed to be on the treatment if the treatment is based on the treatment effect. But if the treatment is based on Y1 only and Y1's got to be greater than 10, he'll be on the treatment. He'll be on the treatment. He'll be on the treatment. Control, treatment, treatment, control, 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 treatment, control. See that? Now these ATTs are all messed up, but that's treatment. That's selection on Y0. What about this one? Okay. D equal 1, treatment if and only if Y0, we'll do it Y0 less than. Now we'll do it basically like that. That's fine. All right. So if your Y0 is greater than 10, you go into the treatment. All right. 1, 1, 1, 1. That's less than 10. That's less than 10. Less than 10. Less than 10. Less than 10. Greater than 10. Less than 10. You see that? You see how it is? So you have selection based on like, is this variable above or below some number? And what that's going to do is like, look, so this was selection on Y0 equal average Y0 for the treatment group 16 equal average Y0 for the control group. And it creates, so whatever it selects on, anything it selects on, the distribution of the terms are going to be different. If it was selecting on race, only African Americans go into the treatment. Well, then if you took the percent of the treatment group that is African American and you took the percent of the control group that is African American, the means will be different, right? So anything that it selects on will automatically create differences in the potential outcome. If it's selecting on that potential outcome, it'll create differences. Does it mean that if the treatment assignment rule is not related to potential outcomes? Yeah, exactly. If it's selection based on race and race has nothing to do with potential outcomes, it won't be a problem. It won't be a problem. And so let's kind of look at this, all right? So here's sort of the big picture. The weirdest thing about causal inference is that, you know, the better our programs are that we design in society, the better our policies are, the better humans get at putting people on the right treatments, the more interventions, target people correctly based on gains, the worse the selection bias is. Yes, pi changes based on the selection rule. Great. Very good, Ronald. Exactly. Exactly. So the better the program is, the more that there is selection on potential outcomes. The more that there is selection on potential outcomes, if there is big variation in the potential outcomes, the selection bias gets worse. So but the less efficient our programs are, the more erratic the assignment mechanism is, the more mistakes there are at targeting people with their best options, the easier it is to do causal inference because selection bias will be smaller. We calculate pi as the average of the number of people in the treatment group, right here, 0.45. So the reason for this drive in the natural experiments that came out of Princeton and Harvard, the reason for it was trying to find the mistakes. They were trying to find the errors that were happening, where it was as though people were back in the lab. That's what they were looking for, because if they are in the lab and it's random, that just will automatically delete. I'm going to show you right now. It'll just automatically delete. So they start looking for sources of randomization in the real world. That's what they're looking for. Rather than modeling the selection bias, they're looking for the randomization out there because they know if they have randomization, what it'll do. They know with almost no assumptions needed, if you have randomization, it will always delete the selection bias. Okay? So, all right, here we go. So this is the notation for randomization, right? This is the notation for randomization. It's not called randomization that I've seen in statistics, although I wouldn't be surprised if I found somebody that did, but I think it's technically just called independence. All right. So we have over here on the right, D, treatment. We have over here on the left, the potential outcomes. Okay. I'm going to write something down. Independence is like a regression model where the treatment does not depend on the potential outcomes, like this. D equal A plus BX plus error, but not Y0 or Y1. Okay? That would be independence. It's not independent of X, which is what somebody asked. Yes, Artie asked about what if it's based on X. Okay, it's not based on the potential outcomes, but it's based on something else. That will be fine. That will be fine. Okay? Treatment can be based on X, but this assignment right here says that it's not based on those two things. Okay? So this would be a violation. This is a violation of independence. It's that selection stuff. D equal A plus B, BX plus D, Y0 plus error. Here, that right there would satisfy this. You would have independence of Y1 because, see, there's no Y1 in the equation, but not Y0 because there is a Y0. Sorry. Oh, my bad. Yes. No, I messed up. It would be independence with respect to Y1, but not Y0. Okay? Not Y0. So if you can imagine that the treatment is based on the potential outcomes, then you can't put that potential outcome over here. Okay? Can't put it. So I don't have it there because it's not independent of y0. It's not independent of y0 because, you know, it's directly related to it. Okay? It's directly related to it. But here, this is like full independence. So that's going to mean this. Treatment isn't based on y0, y1, or treatment effects. y1 minus y0. It's not based on any of them. Yeah, that's right. It's the proportion of treated individuals. So it should be the number of D equal 1 divided by the total number of people. Not y1, but D equal 1. Technically, Eduardo, that is more than we need. Eduardo says, does it require independence with respect to all characteristics? The answer is no. It requires independence for causal inference. For what I'm about to show you, it just requires independence with respect to those two things. Okay? Not all the characteristics. Here. That violates independence. That doesn't. So see right there, Eduardo, treatment is based on the characteristics. It's just not based on the y0, y1. Okay, and here's why we need this. This is why we need it. Okay, so that's a violation right there, and that satisfies independence. If you have independence, okay, let's say it was like this, race D. Okay, let's say it's Asian. Okay, Asian. Treatment assignment. We are putting people into small and large classrooms for various reasons, but we're not doing it based on whether they're Asian. All right? If that's true, the percent of the treatment group, the percent of small classes that are Asian is the same as the percent of large classes. Percent of the classes that are share, yeah, that's it. Share of here. Expectation, probability that you're Asian, conditional on being in a small classroom is equal to probability that you're Asian, conditional on being in a large classroom. All right. Thank you, Miguel. So here, so if you have independence with respect to a characteristic, then the distribution of that characteristic in the two groups is the same, right? You can calculate it though. The thing is though, when it's with respect to an observable characteristic, you can just go. You can look at all your small classrooms and say what percent of them are Asian. You can go to all your large classrooms and say what percent of them are Asian because it's observable. But see, with potential outcomes, it's not that easy. If you have independence with respect to y0, y1, then you can do the same thing I did here, but do it for potential outcomes. Expectation y0 d equal 1 equals expectation y0 d equals 0 if treatment is independent of y0. Okay? And expectation y1 d equal 1 equals expectation y1 d equal 0. Now, why is this such a special? Why is this so important? Why is this so important? Okay. All right. So we're going to write that down because here's why it's important. I can never know what this is, right? For the people in the small classrooms, I would not know their outcome if they were in the large classes. Exactly. Anna just nailed it. But Anna just nailed it. True. for a group of people, I do not know, they're impossible to calculate counterfactuals because they don't exist. But if the treatment has nothing to do with this, I know that whatever that is, it's equal to the thing I can see. No, parallel trends is not about independence. We're going to get to that in the second workshop, but independence will give you parallel trends, but you don't need independence to get parallel trends. Yeah. At the population level, Mauricio, at the population level, look at what selection bias is. Okay, look at what selection bias is. Expectation Y0 for the treatment group minus expectation Y0 for the control. But if the treatment is random, I can write this down. And even though I don't know what that is, it doesn't really matter. Not in that small sample. It's more of a central limit kind of treat. It's like a large numbers. You can always have like you'll have statistical noise in the finite samples. So, but in the asymptotics, it's exactly equal. Right. Okay. So expectation Y0. So I don't know that, right? So it's almost like it's really extreme when you think about it. It's like, oh. It's like, you don't know that. You don't know that. Okay. All you know, the only thing you know is that number. So that might be a 10. Maybe that's a 15, right? But you're like, I don't know if I have selection bias because I don't know what that is. Well, guess what? Under a coin flip, the mean counterfactual will also be 10. 10. How do you know? Because that's what independence does. Independence gives the same distribution of those characteristics in both groups because the treatment assignment has nothing to do with it. No, there's no test. There's no test because you don't have the data. You don't have the data, and it's not based on intuition either. You have to know the treatment assignment mechanism. Only randomization will give you this. Only randomization will give you this. I mean, I actually have been thinking about this for about 15 years. I still don't know. Okay, technically independence is the only thing you need is independence with respect to Y0, Y1. But the only way I know to get independence with respect to Y0, Y1 is just to randomize. And if you randomize, it gets back to what we said before, which is it's not just going to be Y1 and Y0 that are equal. It's going to be race. It's going to be age. It's going to be sex. It's going to be religion. It's going to be all kinds of stuff. So it's like randomization almost gives you more than you need, but I don't really know what in the world would be the treatment assignment mechanism that's only with respect to the potential outcomes. But technically the thing is, there's no reason to write down requirements that you don't need. You only need this, okay? So we write down these two equalities and we're going to hold on to them. There it is. Okay, so the average of Y1 for the treatment group, that is equal to the average of Y0 for the control group, that, so it zeroes out. No selection bias. But what about this heterogeneous treatment effect bias? What about that? All right, so how does randomization affect heterogeneous treatment effect bias from that third line? To see it, let's take our definitions of the ATT and write them out. ATT equals expectation Y1 for the treatment minus expectation Y0 for the treatment. ATU is expectation Y1 for the control minus expectation Y0 for the control. Okay? Now this is the interior term. This doesn't matter. This doesn't matter. So here, the interior term, we're going to write it out. Then we get this minus that. It's going to flip the signs here. So this will be positive, negative. This will be negative, positive. Okay, because it's going to go ATT minus ATU. So we're going to rewrite it. Expectation Y1 for the treatment group minus expectation Y0 for the treatment group minus expectation Y0 for the control group plus expectation Y0 for the control group. Now look. Remember that? Under independence with respect to Y1, the means are the same in the two groups. Well, that mean is observed. That mean is not observed, but whatever it is, it's equal to that, so it cancels out. And there's our selection bias term again. Y0 for the control group minus Y0 for the treatment group. They're equal to each other. It's a 0. So gone. Independence, full independence, will also delete the heterogeneous treatment effect bias. And what does that therefore mean? What that means is that if you have a randomized experiment, you can take the average outcome for the treatment group, you can subtract the average outcome for the control group, which is not a causal measurement, and yet it will be an estimate of a causal parameter. Exactly. No, selection bias doesn't. Independence does, Mauricio. Independence does. You can still have selection on Y1. So you need to have all of it. You gotta have independence with respect to Y0 will get rid of this. But if you still have selection with respect to Y1, a bunch of this stuff comes out and you end up with like a expectation Y1 term that's weighted. I was actually going to give it to you as a homework assignment. So you have full independence with, you call it the identificate. What exactly is this identifying under full independence? It's identifying the average treatment effect. Even though it is impossible to calculate that, randomization lets you calculate it. That's why it was such a special discovery. That's why Fisher and Neiman were like, we got it figured out. Here's the notation. Here's the randomizing device. When you put that randomizing device into this notation, look at all the terms that start getting deleted. And the only thing you're left with after that is this parameter that you probably care about. You want to know the average treatment effect. Okay? All right. So this is what would be kind of interesting, everybody. What about partial independence? All right. So for homework, I'm going to try to remember to do this homework. I have it written down, but I'll do it again. Let me write that. So homework, it's going to be, write down what the STO equals with these two terms. I should probably rewrite it. So it's like, scenario 1, or I'll call it bullet 1, Y0 D. Independence with respect to Y0, but not Y1. Okay. What does STO equal? Bullet 2, Y1 D. Independence with respect to Y1, but not Y0. What does STO equal? Okay. We showed Y0, Y1 D. Independence, full independence. But I want you to work out the partial independence. okay? And see what the simple difference in mean outcomes does. All right. So we nailed it. So 15-minute break, 15-minute break, and we'll come back and then we'll do the last 45 minutes. And we're basically done. I mean, it was a slow day, but you can see kind of why I do it like this. If you go fast, imagine if I'd gone fast and you would just be like, I'm lost. I don't know what any of this is. And so my experience has been you really cannot go slow enough. If you just force people to go through spreadsheets, they will always benefit from it, no matter how well they think they understand it. It's always something new that they've not seen. Okay, so let's take a 15-minute break. We'll come right back. My window is doing it. All right, I'll be right back. All right, so I think that what will help, I'm sorry there's so much light on me, is homework assignments. And so I've got two here. All right. Oh, where'd he go? What did I do? Oh, yeah. That was where it was. Okay, so homework. First, I want you to do a homework assignment where you're going to see what the SDO equals if the treatment assignment is based on Y0 but not Y1. You're going to write that down. You're going to write down the equalities that you can write down based on that independence assumption, and then just plug it in to the SDO. Just plug it in. People that wrote me and they're feeling a little bit nervous about the workshop, plug it in. It's just all pen and paper. Okay? It's just pen and paper. Then do the same thing. SDO, what does the SDO equal if treatment assignment is based on Y1 but not Y0? Okay, that's 2. And then I've got one more assignment I'm going to give us. My computer would quit being so slow. All right, so classes. Good. Okay, good. So we're going to do this one again. All right, so we'll do that. And then I have another thing. Yeah. All right. I think what we're going to also do is go through an empirical exercise together when we start out based on a large scale experiment. I'll just walk us through it. But for now, let's just, what I'll do is I'll send out an email, but you're going to just do the same thing again. Okay, I'm just going real quick. Okay, so what we will do is we will have that assignment. Okay, you're going to fill all this out. You're going to redo this analysis. If anybody is struggling, redo the analysis. Okay, with new data. We'll do it again tomorrow. I'm going to give you a sheet of an assignment, and then also do the homework assignment. Those 2 things. Okay, and then we'll have a third thing, which will be an empirical assignment. We'll just do it. We'll do the empirical assignment at the beginning of class. Okay, well, so I'll break it out and we'll do this empirical assignment at the beginning of class. Okay, these 2 things that I said, you know, the potential outcomes, except fill out the potential outcomes Excel spreadsheet, both PO version 1 tab and version 2 tab, that is in the labs potential outcomes subdirectory of our GitHub repository. Okay, you're gonna do that. So those are the 3 things tomorrow that we're gonna go over, and then we're gonna also go over the randomized control trial. We're gonna do it together. We're gonna do the randomized control trial together. Okay. All right. So let's start. So we are doing good on time. Yeah, 25. So we'll be able to finish this. Okay, so let's now talk a little bit more about some sort of deeper assumptions that are embedded in okay, Eduardo says, what's going to be it? Perfect doctor. It's going to be perfect doctor. It's going to be assigned to treatment if treatment is non-negative. Okay, same thing we did. Same thing we did. All right. Because that's enough. I think that's enough. I think you start trying to mess with it too much, and you know, we're gonna do in the written assignment, we're gonna do like, you know, independence with respect to this or this, and then kind of work it out. But then what I want people to do is just more experience with a pen and paper, just going, or like, you know, in Excel, just kind of going through multiple times and teach yourself. That's the goal. Teach yourself this. Or, you know, this. Teach yourself that. Okay? Do it over and over until you know, why this is equal to this. You do that, you can do it. You can totally do it. All right? We have not really brought in anything from outside of class. If you think about it, there's not been one thing in this class except for averages. That's really the only thing we've been doing this whole time is just averages. So a lot of what you might be struggling with is just the novelty of this and of just like kind of working with it, but it's worth it to just dig into it. Okay. Yeah. Artie's right. So, okay. Now, when we are actually taking, so we've got these average treatment effects. Okay. And like, that's like our parameters of interest. I'm sorry, my eyes I can't see. I hope that's okay. So, we've got these like aggregate causal parameters, right? But, in order to take data, okay, in order to do this and combine treatment group units into averages and control group units into averages, there's actually these statisticians, Don Rubin in particular, they really worked out every conceivable detail that would allow this to ultimately equal this. And I don't really know the right way. I don't really know exactly how to explain why this is the case. But basically what's going on is even in order for this to collapse into that, there's some deeper assumptions that are needed. And those deeper assumptions that are needed is basically versions of that when a treatment group, when a unit is treated, but actually it's this, okay? Let me say it like this. That switching equation, right? was y equals dy1 plus 1 minus dy0. And what this meant was, what this technically meant was that my realized outcome equaled my potential outcome based only on my treatment assignment, not yours. Okay? Had nothing to do with yours. So if like Ronald, if Ronald gets vaccinated, okay, and we are roommates, then my potential outcomes associated with vaccination, with me getting vaccinated, could be different than if Ronald had not gotten vaccinated. Why? Because look at this, all right? Let's say it's this same. If I get vaccinated, Y1 equals, let's see, it's COVID symptoms, COVID. So it's like, do I get COVID? So it's like, get COVID symptoms. Let's say it's like COVID symptoms. It's and the bigger numbers are worse. It's like it's a 5. If I don't get vaccinated, Y0 equals 8. Okay. So delta equals Y1 minus Y0 equals 5 minus 8 equals -3. Vaccination lowers my COVID symptoms by 3. Okay. Ronald is my roommate. And he gets vaccinated. Okay. Because Ronald is vaccinated, I might not get COVID simply because he's a buffer between me and other people. And that means this: if Ronald vaccinated, if I get vaccinated, Y1 might equal 8. No, 5. If I don't get vaccinated, Y0 equal 5. Maybe Ronald getting vaccinated, exactly, it's an externality, exactly. But see, the statisticians are not economists, so they do not use that word. They do not use that word. Instead, they use the word interference. Interference. And so what is ruled out, okay, if I get vaccinated, my Y1 is a 5. If I don't, it's a 5. Delta equals 5 minus 5 equals 0. I might not get vaccinated now just because of Ronald. Okay. We call it in economics, we call it free riding. Free riding, externalities can kind of create that. But here's the deal. What you're assuming, these kinds of aggregations place limits on what happens when one person gets treated. It can't spill over to another person in terms of changing their potential outcomes. My potential outcomes have to be based on me, and my realized outcomes have to be based on my treatment assignment, not Ronald's. And if they are, it's interference, and it will not allow you to get like a stable aggregate causal parameter. It becomes a lot harder, okay? It's an active area of scholarship, and it's very important in studying social networks, peer effects, and various platforms, because in those situations, there's tons and tons of interference. Even when they do these randomized experiments, there'll be tons of interference. Okay, you put one guy into one kind of treatment group on Twitter, he changes his tweets. All of a sudden, the guy in the control group is kind of being treated, even though he wasn't treated. He's being treated because Ronald got treated. Ronald and I are friends. Ronald's now acting different. That's what Sutva is. Exactly, Jeff. So Sutva is what's kind of a bundle of assumptions. They're a bundle of assumptions related to they're related to the aggregation of data. Okay. And here's what it stands for. It's a horrible acronym. It's horrible, but here's what it stands for: stable, unit treatment value assumption, SUTVA, or SUTVA, but I don't know, there's like not even a real word, so nobody's gonna get mad if you pronounce it wrong. So SUTVA, stable. What does stable mean? Well, here's what it should mean. This is Ronald not vaccinated. Okay? Ronald not vaccinated. SUTVA would mean treatment effects do not vary, potential outcomes do not vary based on the treatment assignment of someone else. That's what it means by stable. Doesn't matter what happens to everybody in the data. I always have the same Y1. I always have the same Y0. My realized outcome is based on my treatment assignment, nobody else's. I am not getting treated when Ronald gets treated. Okay? And it's an assumption. It's called treatment value, not causal effect, because probably if it was causal effect, it'd be like, too many vowels. So, it's not like that. So it's treatment value, but it's the value of the treatment effect because the potential outcomes aren't changing. So a lot of this ends up being kind of having to do with, if Ronald is in the experiment and he's being treated, but Ronald's behavior is directly impacting me, I cannot be in the experiment. I cannot be a part of the data aggregation because I am unstable. My treatment effects are unstable as a result of the other people in the trial. So a lot of the ways that you mitigate this is in the design stage. It's not that you can't have externalities. It's just that the externalities cannot be within the data set. So you can't have treatment group and control group spilling over to each other. And a lot of the ways you do it in RCTs, you might make sure you have to go to great lengths to make sure that the treatment group has no interaction with the control groups. And, a lot of these development economists, they get extreme about it. If you've got to go, well, yes, exactly, you jump. It's got to be that the treatment assignment of one of the groups cannot be jumping over to another unit, whether they're in the treatment group or the control group. Because if Ronald's treatment is like interfering with my potential outcomes, then my treatment effects are not stable because my treatment effects will change simply as a result of what Ronald does. And that will create an unstable aggregate causal parameter. And it's like, it will never, like, it's just like even the average treatment effect will change. Okay. So it's got to be like, it can't be doing it. So a lot of the ways you do it is, you make sure that the comparison group cannot in any way be traced back to the other treatment group, and none of the, and there's no interference, between any of the other units. So it's like, if everybody's in the treatment group, they're all being treated, that'll be like the treatment. Okay. Yeah. So it was applying to the treatment and the control groups. Technically, it's just no interference between the units, but it's got to be like, my treatment assignment is based on my treatment assignment is based on my own, my potential outcomes based on my treatment assignment. And if there's interference between the groups, then it can change things. It doesn't really seem to matter, I think, if they're all treated, but it matters a lot if it goes across treatment and control. I see you topping Strayo sheet, so I'm gonna does unit mean the collection? Yeah, it means like a person. It means a person, Sergio. So it's like if Ronald, there could be 1,000 people in the treatment group, but it's like a 1-to-1 thing. So it's like Ronald's treatment isn't spilling over to other units. You have to just kind of design it in a careful way. Yeah, exactly. Exactly. It really affects the experiments a lot. It affects power. It can be like, you've got to do a lot of things to ensure these guys are segregated. It can affect the quasi-experiment too, but it doesn't have to. Okay, so like you could be doing a study where you're looking at, city laws, minimum wages. And some cities could get the minimum wage. Some cities might not get it. And, where I live, Waco, Texas, there's a city about 45 minutes away called Temple. And then down, so if we had a minimum wage, but Temple didn't, well, it's possible that Temple ends up getting treated because maybe the workers drive to Waco in order to try to get jobs in Waco. Maybe the firms relocate to Temple. All that you got to be careful about is you got to think really carefully about the nature of this treatment and think really carefully about, is there something in the control group that this is probably affecting? Okay. And, some treatments that's probably true and some it might not really matter. Jaywalking laws in one city in Waco, it's kind of hard to imagine some law about jaywalking in Waco having an impact on jaywalking in Temple. But for really big labor market interventions, it's not crazy. If it's changing the cost of production, the firm might change its location. The workers might change where they work. Okay. So there's another thing that's contained in SUDVA. It's called no hidden variation in treatment. And think that I kind of mentioned this earlier. In Y1 and Y0 for the binary treatment, each is associated with a clearly well-defined treatment dosage. Okay. So it's like, I take at night, I take melatonin to help me sleep. It's an over-the-counter sleep aid, and I take it to help me sleep. So I take a lot actually, because they're in these gummies and it tastes like candy. It's probably thankfully you can't hurt yourself with melatonin, but that I'm aware of. If I haven't ever gotten to the lethal dose, but I do eat them like they're candy. And so let's say I take 30 milligrams. You're supposed to take 10. I take 30. Okay. I take 30 milligrams of melatonin. But let's say Ronald takes 5 milligrams. Okay. Okay. What does D equal 1 mean? Does it mean 30 milligrams or does it mean 5 milligrams? It has to be the same dosage, has to be the same dose for all people for it to be classified as D equal 1 or D equal 0. This is easy to control in a randomized experiment. No, it's not the same thing, Ollie. That kind of IID assumption is not really talking about, there's no randomness here. It's not like a random draw, like from the distribution that does these shocks. Rather, it's basically saying, when Ronald gets treated, he doesn't like come over to my house and like hang out with me and then inadvertently treat me because, he's doing really good on the treatment. I mean, there's all kind of stuff like that could happen. Like, yeah, exactly. Uterate. So exactly. Network effects, peer effects, externalities. There's lots of examples of this. SUDVA, Robinson, this would violate SUDVA because SUDVA assumes that the D treatment status is consistent for all, anybody that gets the treatment, it's consistent. Now, if you have multi-valued treatment, you might just have D equals 0 means, no melatonin. D equal, you could have this. You could have like, D equal 1 might mean 5 milligrams. D equal 2 might mean 30 milligrams. And you just model the multi-valued treatment as best you can. Okay? As best you can. Now it does become practically very hard. There is an area of work on continuous treatment. Let's just kind of put that aside though. All right. It is extremely easy in the social sciences to violate this. Let's say that you're studying the effect of hospital quality on, no, sorry, you're wanting to know the effect of hospitals, like private hospitals or something. What was that? I don't think this is exactly what I was wanting to do. So if you're wanting to know like the returns to a public hospital, okay? You could imagine hospitals vary in quality within that public hospital. They might vary a lot. Some might be very good. Some might be very bad. Staffing might be different in all of them. There might be some negative selection in some of them with respect to certain kind of staffing, certain kind of resources, and so on. So this kind of stuff is like almost guaranteed to be violated. The only way you really can do it is if you can kind of, if there is like reasonably coarse, you know, things that you can do, you might want to do that. But lots of time, it just might require you just being very, very explicit about what is being grouped together. Okay. But, you know, you still have to be very careful with this, because if you start grouping things together that are just very different, it doesn't really have a causal interpretation, or the interpretation could be very misleading. You could have like, you know, what's the effect of cannabis on student test scores? And for like 10 people, it's like, you know, an edible of some amount. I don't know how they're measured, but like some amount of THC or whatever in the treatment group. And then there's like 5 people for which it is a very powerful strain at a very high level. And, you know, you've mixed them. And so like one group could have a very different group of treatment effects associated with that dose that's very different than another. And it's like they both get kind of average and you don't really know how to interpret it. It's much easier to interpret if it's homogeneous. Okay. There is work on continuous, but we're not going to get into that. Okay. So that's something there. And then the last thing is scale. Scale can affect the stability of the treatment effects too. So it's easier to kind of just explain this with an example. So I said I live in Texas. So imagine Texas has some early childhood intervention. It's like a curriculum, maybe for like 5-year-olds. Somebody in Texas develops it. It's like, you know, done in Texas. Maybe it's even an RCT. Maybe it's a large scale RCT throughout the whole state. Okay. And they estimate the causal effect of that early childhood intervention, and they find these big returns. Maybe the president of the United States reads the article, goes to his, you know, staff and says, I want you to get this rolled out to the whole country. This is going to be a part of my, you know, my presidential campaign. We're going to get this done everywhere. You could find very different effects at the national level, and not just simply because the samples are different. Okay. Scaling up a policy can be very challenging. Okay. Maybe when President Biden rolls out a program for the whole United States for all of its 5-year-olds, he can't find the same quality teachers nationally as they found in Texas for the experiment. Maybe in Texas, they had the experiment was the curriculum and teachers that had at least 10 years of experience. Okay. But Biden cannot, eventually there are not enough teachers like that. So he has to start hiring teachers with, you know, less experience. I shouldn't say lower quality, less experience. Well, it's not the same treatment at that point. It's a variation really it's really a variation on this thing, no hidden variation treatment. Texas did one program, Biden tried to do it, and it's not the same. And in economics, they kind of talk about these things all the time. They talk about things like the cost of production being rising, flat, or falling, rising, increasing, or constant. And that's like another way of talking about things that can violate SUDVA. And so, you know, a lot of this just means that, you know, it does get a little difficult to extrapolate these things a lot. And so we can kind of infer things internally that are correct, but our ability to extrapolate it might be challenging if we're trying to scale, if there's hidden variation in the treatment, or if there's interference. It becomes harder. Well, first of all, I can't even do it. And then like to extrapolate, it gets kind of hard. Okay. I see some people typing. So we have like 15 minutes and I'm going to see what these are. And then we're going to discuss a paper. It is generalizable under certain conditions, and you have to make sure those conditions hold. That's all. So it's like, if SUTVA holds, then you'll be able to identify, you'll be able to say something about those causal effects out of sample, so long as the out of sample population is similar to the in sample population. Then yes, under SUTVA. If you lose SUTVA, you lose a lot. Yeah. Yeah, exactly. And really, I think so Shreyoshi is this, I think the other thing we forget in these scale ups, and this is like another way of talking about external validity, is to say this concept of information, you could learn from the mistakes of what happened in Texas and change the policy. See, and this is kind of getting at some of these themes where it's not you're introducing heterogeneous populations. You know, the population is different now. Why? Because there's information that's been learned in the population, or maybe the treatment is not the same. And if the treatment is not the same, you've got hidden variation in the treatment. All right. So you kind of have to have it be like, you know, we learned that there were mistakes, we fixed them. Well, if it's not the same treatment, then whatever you learned internally, you know, you have less ability to extrapolate. It has less external validity. Then there's a lot of ways in which, you know, this does get pretty difficult. Okay, it does get pretty difficult. I want to spend a couple of minutes on a paper that I hope will inspire you and kind of bring some stuff together. Okay, this is a paper that was published in the Econometrica, which is a top journal in economics. And it was published in 2015 by Thomas Blake, Chris Nosko, Steve Tadalis. Nosko and Blake were on, well, I know Nosko was an assistant professor in the marketing department at the University of Chicago. He was an economist. He was there, and I don't know where Blake was. But Steve Tadalis was a professor in the business school at the University of California, Berkeley Haas Business School. All three of them, Nosko took a leave from Chicago and became like he went to go work for eBay on leave. This was at a period of time the tech industry really kind of started hiring PhD economists in large mass around 2010. It's when Susie is like, Hal Varian goes to Google kind of earlier than that. Preston McAfee goes to Yahoo, and then Susan Athey goes to Microsoft. All three of them originally micro theorists. They're working a lot on auctions and the search engines, but then there's like a shift, and even outside of the search engines, people are getting hired, but a lot of it is the auctions. So this is eBay. So a lot of the early hiring of economists was with these guys that knew auctions. So they leave. Blake and Nosko go to eBay. They're on leave. I don't really know what the title would have been, but Tadalis is like principal scientist, okay, at eBay. So they're all on leave and they go work there. And Nosko is now one of the chief economists at Amazon. And I interviewed him when he was like director of product or something at Uber. So he's kind of been one of these guys that's had these like pretty illustrious tech career. There's a few of these economists that are like that, kind of steadily have risen up. And he's kind of like a second wave of the more causal inference people. Okay. So this is a paper that started that was at eBay. And let me tell you a little bit. It's about advertising. Okay. Here's some facts. All this is from the paper. And the facts are 10 years old. Okay. So I don't know what the new data is. So in 2012, revenues from internet advertising was 36.6 billion. Presumably it's only gotten bigger. Okay. But there is a particular kind of advertising on the internet called search engine marketing. And here's what would be search engine marketing. eBay typewriter. I don't know which of these is the ad. I don't know why I don't see advertisements. Maybe I have them blocked or something. But anyway, so sponsored. Here we go. I think these are ads. Okay. These are ads right here. And then this is like organic. Okay. So there are like different kinds of ads that you can like, you know, purchase. So like I could purchase an ad. It's like if anybody, you know, Google's workshop, mixtape sessions, workshops would show up. And I'd like, you know, I'd have to bid on it and all this stuff, you know, and so like, you would see my thing if that came up. Right. Well, so if you type in branded keywords, right, it'll bring up these sponsored things versus like typewriter for sale. Typewriter for sale is going to bring me more stuff. It's going to be Etsy, Office Depot, Staples, a bunch of other stuff, but not just eBay. Not just eBay. So paid search is where you are having auctions on the search terms and they're branded. Okay. It's the largest format by revenue, or they're not always branded, but that's what this paper is going to be about. So it's the largest format by revenue. It accounted for about $17 billion of that 37 billion, or almost half. And Google's the leading provider. They had $46 billion in global revenues in 2012. 95% of that was from advertising. Okay. There's selection bias. If you compare the spending patterns of people who typed in typewriter for sale and went to eBay, okay, if you compared those people who typed typewriter for sale versus people that typed in eBay typewriter, okay, we might both click on the exact same thing through the ads, okay? Or it could be typewriter for sale, could be that I go just here, use typewriters on eBay and get there, okay? If you just compare average spending patterns for people who clicked on the ad after typing eBay typewriter compared to average spending patterns for someone who did not get to eBay through paid search marketing, okay? There's like a 1,600% return on investment estimated if you in that comparison, okay? In that comparison. But the thing to remember is that it's not random that people are typing in eBay, ... right? So if I type in eBay typewriter, I am almost certainly trying to get to eBay, where the typewriters are. Why? Probably because I'm trying to buy from eBay. So I typed it in. Whereas a person who got to eBay through the organic search, through PageRank, it's not clear that they're going to necessarily, it's not clear that they're committed to buying a typewriter at eBay, even if they are committed to buying a typewriter. They might be shopping around. Okay. So the problem is that the ads are targeting people at the end of their search process. They've already decided they're getting a typewriter and they're getting it from eBay. So the question is, would they have gotten to eBay anyway had they not gone through the auction? That's what selection bias looks like here. Okay. So they do a study where all they do in this study is they regressed spending at eBay by comparing people who clicked on, people who got to eBay through paid search onto a dummy. Oh, yeah, that's the dummy. To those who didn't, controlling for fixed effects, time and location fixed effects. And then when they do that, they get a 1,600% estimated return on investment. These guys convinced eBay to run a randomized control trial, a large field experiment, massive field experiment, where they randomly assigned whether or not you would see an auction, whether you would see an advertisement, even if you typed in eBay typewriter. And when they did that, they found a negative 63% return on investment. The treatment is going to be seeing an advertisement. It's going to be this. So some random group of people will see that ad and some won't randomly. They'll see the ad, even though they're typing in eBay typewriter. Some of them will only see this like organic stuff. Organic meaning it's not an ad. And then some of them will see the ad. So they're going to randomly show people ads and see what happens to their spending. Okay. How did this study get done? The three of them were well trained in causal inference. They come from Harvard. All three of them did. Even Dallas did. He started out he did his PhD at Harvard. So he goes to Berkeley. So they're all three kind of like Cambridge, which is really another place where causal inference, blossomed. And they are like walking around or something like that. And they overhear like an accountant or something like that basically describe a natural experiment. They said eBay had stopped paying for branded words on Yahoo and Bing, but not Google. Blake, Nosko, and Tadalis begged for the data. They got the data, and this is what they found. This is Google. Clicks to eBay. This is Microsoft. At this point right here, they quit paying for branded search. This is people getting there through the auctions, through the ads. This is people getting there not through the ads. And look what they found. They basically found that you can't get to the ads anymore. You're still typing in eBay typewriter, but you can't get there through an ad. But look, all of a sudden, there's a big increase in people getting to eBay through this. If they can't see this, they just go to eBay still. They were always planning to go to eBay. Okay? And what that means is that even if they hadn't seen the ad, Y0, they still would have gone to eBay. Okay? So that means you've got selection bias based on that Y0. Another experiment they found was that in Germany, Google, they quit paying for Google. You found the same thing. This is a difference in differences design, and this is just an interrupted time series. When they quit paying for Google, obviously nobody can get to, eBay through Google ads, but they still get to eBay through, it's like whoever was going to do it there, they just get there anyway. So this is a sign of selection bias. So the evidence strongly suggests the intuitive notion that for branded keywords, brand meaning eBay, something, natural search is almost a perfect substitute for paid search, making branded keywords of search engine marketing basically not effective at driving sales, at least in the short run. After all, any user who typed in eBay typewriter into their search engine probably was intending to go to the website, probably was intending to execute something, regardless of whether they saw an ad. They're basically saying that they're typing in eBay typewriter in order to navigate to eBay. And if they see an ad, they just go that way. If they don't see the ad, they just go through the other one. They're using branded keywords to navigate. So they're bidding on stuff that's like a waste of money. They were already going to buy anyway. All right, so look, this is what they end up doing. The natural experiment was very valuable. The natural experiment was very valuable, but it was very valuable because they were able to, Dallas, Nosko, and Blake were able to go to the CEO and the other executives and convince them to do a gigantic RCT. Because if they are spending as much money on these, this is a lot of money they're bidding on. If they are spending that much money and they are not getting a 1,600% return on investment, they're just burning cash. Okay. So they used it to convince them to do an RCT. And here was the RCT. They randomly assigned 30% of eBay's US traffic to stop bidding on all branded keywords for 60 days. Okay. For 60 days, they do this RCT where certain geographic markets simply do not get ads. Okay. A random group of users were exposed to ads. A control group didn't see the ads. And they used the geographic bid feature to accurately identify the geographic market. And they did only 30% because eBay was afraid. If there really is a 1,600% return on investment and they quit bidding on this, they're throwing away money. So it's a very, it's like probably they're sweating over this about, how this could really go bad. It could be really expensive. If they find that there's a 1,600% return on investment doing this, that was the most expensive experiment in the history of man. Okay. So here's what they find. So if they do the simple, non-experiment, okay, they regress spending onto a dummy for whether or not they got to eBay through an ad. They get a coefficient of 0.126, doesn't matter what it equals, but this is the return on investment. When they put in the fixed effects, they still find a 1,600% return on investment, and then the confidence intervals go from 697 to 22. So it's huge. They can reject zeros, but remember, simple difference in mean outcomes, and even with these fixed effects, it's still going to have that selection bias. The selection bias is not going to be zero just because you put in fixed effects. Okay. So then they do the RCT. Now look, those coefficients start with a 1. That starts with a 0. The second thing's a 0. That's a 6. 12,600 versus 659. This is a fraction of the magnitude. This is basically a precisely estimated null, a 0 effect. When they use that coefficient, they compare it to spending, they find a negative 63% return on investment. They do not find it. Why are they doing this? Why does it do this? Because I'm just going to stop there. So what's going on? Okay. This is targeting people this is an intervention that is targeting people who were already going to buy, even if they hadn't seen the auction. And it was giving a spurious result. You had selection bias baked into the data. And a model doesn't fix it, but independence fixes it. Okay. You have to change the variation in the treatment. You have to change the treatment assignment mechanism, not change the model. The more that you change the model, the more it's going to be model dependent. Okay, but if you can find variation in the data that comes randomly, it'll eliminate the selection bias, and nothing's going to do it better than an actual randomized experiment. Okay, so the natural experiment was valuable. Okay, it's just that natural experiments oftentimes don't have nearly the same certainty that an actual physically randomized experiment will have. Okay, so we use natural experiments though, because most of us don't have the ear of the CEO letting us run RCTs. Okay, so Pizza Hut, I don't know if they're running RCTs on their crust or whatever. I don't think they are, but they're probably in there's probably like 1,000 Pizza Huts or something in the United States, and and probably like 4,000 counties or something. I'm just making that up. So they don't probably run randomized experiments because they're franchised and they have a lot of autonomy, but they're in a bunch of geographic markets. So natural experiments might be more useful, like difference in differences or synthetic control. So the RCT is valuable. It's just, and it's the best one in a lot of ways, but you just can't it may not be ethical to run the RCT. It may not be practical. It may be too expensive. So in a way, it's like we have to look at other methods and other ways of finding treatment assignment that are just practically useful. And in the area of public policy or, major things like education or college or marriage or divorce, it's, you can't do randomized experiments on marriage. Can't do randomized experiments on policing. Nobody's gonna, rarely is anybody gonna let you do those RCTs. So that's where we go from here. Where we go from here is we go into a set of tools that is going to let us work to estimate those causal parameters that we discussed, even though we are not inside the lab. Exactly. The RCT eliminated the selection bias. It showed that advertising did not increase revenues in the short run. It did not, because what it did was it made equal the average potential outcomes in both groups. And so then you just do simple comparisons and you have an estimate of the average treatment effect. But when you're putting in fixed effects, it's a pretty blunt way to go about trying to solve the causal problem, because it's like rather than finding random variation, you're just trying to say, well, I'm going to assume that the selection biases can be controlled with this dummy. And that's extremely, extremely optimistic. That's very optimistic. A lot of the selection that we are worried about is not that easy to deal with. Okay. Yep. Exactly. They would have had more profit by not advertising, not using search engine branded advertising. It's not that they shouldn't advertise. It's the branded advertising. Don't bid on eBay typewriters. You can bid on typewriters. When people type in typewriters, you can bid on that, but don't bid like on eBay typewriters. In fact, maybe don't even participate, potentially. Not sure. Actually, yeah, that is true. They're typing in eBay typewriters. They might see ads. They're going to go to eBay because that's where they're trying to go. All right. So what we're going to do tomorrow is we're going to do these causal graphs called DAGs. And we're going to use these DAGs to motivate to motivate the use of covariates. Okay. And then next week, we're going to use those DAGs to motivate the use of instrumental variables. And that's the goal. So I'm going to write it once I can see, because the sun's in my eyes. Once I can see, I'm going to kind of write up that homework assignment, get it to y'all. In the meantime, you can go ahead and be working on that one homework assignment, but I'm going to give you the homework assignment for the spreadsheet. Okay. I'll give you that. And then I want you to do that tomorrow. We'll just go over it together. Is that cool? Gosh, man, I gotta get the lines. All right. Well, you guys have a great day. Thanks for being so engaged and all your questions. And as soon as this is loaded up to Zoom, I will upload it. Okay? All right. Bye, guys. And I think you'll be able to do when I get the AI chat, I'll put the AI chat in our Discord. Okay?